Let's move into the lecture. So yesterday, we actually didn't quite finish the lecture. So I'm going to go back to where we left off, which was here. And we're going to continue the rest of yesterday's lecture. And then we move into part 2. So yesterday, we started our journey into multi-agent deep reinforcement learning, which is where all the current action is. A lot of excitement, a lot of research. And that's why I think most of you are here. And there's in particular a type of approach called value decomposition that has received a lot of attention in the past few years, and which is important for certain classes of games. So we're going to be talking about the basic methodology, how it works, and give you some examples of algorithms that do this. And after that, we take some questions and then move into the second part, the final part, and try to get as far as we can for the rest of the day. Okay, so as always, raise your hands if you have any questions. Feel free to interrupt me. So we've addressed Marl challenges and policy gradient by using these centralized critics. You remember what that is? Multi-agent policy gradient means that we implement policy gradients, but we have this idea that there's a centralized piece of information that we can all use in a centralized critic. For example, everyone's observations or the jointly observed state, some privileged information like that. And then after training, we don't need the critic anymore, so we can leave it behind, and we just have our policies that we can train in a that we can execute in a decentralized way. So now we did this in policy gradient algorithms, but now there's a question: can we do something like that in value-based algorithms, like Q-learning, for example? Okay, there's not a policy gradient. There's not this idea that I'm directly optimizing a policy. Instead, what value-based approaches do is they learn these value functions, like a Q table, a Q function, and then they derive implicitly the policy from that by having a greedy policy with respect to the value function. So that's what it says here. In value-based Marl algorithms, like independent DQN, we saw that yesterday, the agents learn the value functions and derive their policy from them by making it greedy, for example. But in learning and deriving a policy from centralized value functions would prevent decentralized execution. So if you are in a situation where your policy is derived from a value function, like a Q table, like a Q function, then if you want to do this when you execute the policy, you need to have all information locally in place in order to query your Q table. Okay, I think that much makes sense. But if we're using a training regime where the Q table is using privileged information that is shared, then I don't have that anymore after training. When I then execute, I don't have this shared information anymore. For example, everyone's observations. So that kind of idea that we did before yesterday doesn't work anymore here. Okay, we need something else. So how can we overcome this limitation and leverage the benefits of centralized value functions that have this privileged information in value-based Marl algorithms like Q-learning, for example? Okay, so that's where value decomposition comes into place. And so the idea with this value decomposition is that we want to decompose a value estimate for an action into the individual contributions of the different agents. That's why it's called value decomposition. And it's useful for a number of reasons. For example, we can address problems like multi-agent credit assignment that we already saw. And here we're focusing on common reward games. Remember, these are the kinds of games where every agent gets the same reward. So it's a common reward. They have the same reward function. So these methods decompose a centralized action value function for all agents. Okay, let's go through what this means. This is just a reminder. This is the Q function, which takes as input a history in the game so far, including, for example, the most recent observation or state. There's some privileged information during centralized training. And then there's a joint action here that we're trying to evaluate. Theta, as a reminder, these are the parameters. We use theta for value function parameters and phi for policy function parameters. So this is now all using theta. And what this gives you is the expected discounted return. So the sum of rewards over time with the discount factor, if we execute that joint action and then follow the joint policy subsequently. So we want to decompose this expectation here into individual utility functions for each of the agents that we have. So for every agent I in the set of agents, we want to now have a function like this that is specific for agent I's theta parameters. And the decomposition means that basically there's a breakdown of this bigger function into these smaller individual functions for each agent I. And there's a few different ways of doing this, which we'll see in a minute. But this decomposition has several benefits. Agents benefit from centralized information during training. This is what we had yesterday. We want them to leverage shared information like the joint observations, for example. This is a privileged situation, basically. It simplifies learning by decomposing the centralized value function. We have smaller value functions, which are easier to learn, hopefully. And agents learn their individual utility functions to present their contribution to the centralized value function. So that's what I just meant. We can address the multi-agent credit assignment problem if every agent understands a bit better what their contributions is to the longer-term reward. Okay, there's an interesting property here that you need to be aware of, and that sort of features in many of these methods. It's called the individual global max property, or IGM property. So how do we ensure that the decentralized action selection during training or after training, we need to have the ability to choose actions independently of one another? How do we ensure that we can do this with respect to the agent's individual utility functions? So these are the decomposed functions that we want to learn. So that when they choose their actions individually based on their own utility functions, the collection of these actions is still optimal with respect to the centralized action value function that we decomposed. Okay, so there's a bigger Q function that we assume there is. We decompose that into every agent's own utility function, and the bigger function is a function now of these individual utility functions. We want to make sure that if the agents choose their own action using only their component of this decomposition, that the collection of these actions, when you take them together, is still a greedy or optimal action with respect to the original decomposed Q function. Does that make sense for everyone? I think it should make sense. But basically, this is a property that we need to be aware of and that we want to guarantee, right? Because if we don't do this, then we have a decomposition. And then if the agents use only their part of the decomposition to choose actions, if this guarantee doesn't hold, then the combination of their actions might be some weird stuff, right? It might not be good, actually. So we want to have this kind of guarantee. Okay, so solution. Let H be a full history, which has all the information that's happened so far. It's a theoretical construct. It's not necessarily what the agents observe after training, but for example, you might be able to see this during training. There's just a reminder of notation. Joint observation histories is only what the agents individually observe. So there's this function sigma that we introduced. You apply that to the full history and you extract only the local observation histories. Then there's individual observation histories with respect to every agent I. Just a reminder of notation again. So it's the same function sigma I. And then there's the centralized information Z. For example, you can observe directly the state or you have some other privileged information. So the individual global max IGM property is satisfied if and only if this thing holds here. What does this mean? Step by step, let's go through this. First, for all join actions, remember a join action is a tuple that contains an action for every agent in the system, 1 to n. For every join action, if the join action is in the set of optimal join actions with respect to the decomposed value function, then it must also be the case that for every individual agent I in the system, its part of that join action is also optimal with respect to its own individual utility function. So this A star set here is all the greedy actions with respect to the bigger Q function, the one that we decompose. And then this A star set for agent I is the set of all the greedy actions with respect to the decomposed component for that agent I. Okay? And so basically what it means is that if we have a join action that is up greedy with respect to this bigger Q function, then each of these individual agents' actions will also be in the greedy set for the decomposed component for that agent. And so conversely, that means that if they do pick their own greedy actions only with respect to their individual components, then we know for sure that the combination of their actions is also going to be a greedy join action with the original Q function. That is the main property that we want to satisfy. And if this is satisfied, then we know that after the decomposition, the agents can go ahead and do their action selection only using their own component that they learned in the decomposition. So upholding the IGM property has two important implications. That's what I just explained. If all agents decentrally select actions that maximize their individual utility functions, the thing that they extracted from the decomposition, the resulting join action will maximize the centralized action value function. So That's important. That's what I just explained. And the greedy join action with respect to the centralized action value function can be efficiently obtained by selecting the greedy actions for each agent with respect to their individual utility functions. So that's important for efficient training. Okay, there's a little note here as well. I guess you need to be aware that not all environments admit such a decomposition, and we're going to see some very basic matrix games where we see that different types of compositions sometimes succeed and sometimes they're not able to do the decomposition. So this note will be clear in just a minute when we look at some examples. Okay, here's the very first way of doing this. It's probably the simplest way. It's a linear decomposition. It's the first algorithm that was kind of proposed in this spirit. It's called VDN, which stands for Valley Decomposition Networks. But probably a better name would have been something like linear decomposition networks, because that's what it is. Anyway, it looks like this. So here we have our big Q function that we want to decompose. And the decomposition is very, very simple. It's just directly a linear decomposition where basically the Q value for a particular join action is decomposed as a sum of individual Q values for the actions of the individual agents I. Okay? So you just take the sum over the agents and you just sum up the Q values for the individual action values. And that is then together, the sum makes up the value for the join action. Linear decomposition, very simple. Okay, this decomposition satisfies the IGM property. And we can jointly optimize the parameters of all networks by minimizing the following loss. Looks like this. So you have your replay buffer, and you can sample your batches where there's B elements in every batch. So we take the average over the batch. Every experience in the batch looks like this. There's the history collected so far, or this could also just be the state, join action, reward, and then the successor history or state. And this looks very familiar already. Here we have our basically our Q-learning target that we saw previously, where there's the immediate reward plus the discount factor gamma times. And this now would be the value attributed to the maximizer action in the successor state. But because we have this linear decomposition, we actually sum over the maximizers for each of the individual agents components. That's why it looks like this now with the sum rather than before when we didn't have the sum here. And then you subtract the original estimate, which is again a sum because it's a linear decomposition. So basically this linear decomposition that we defined up here is just mapped into the TD update targets that we saw before. And that's why these sums appear now inside here. Okay, but other than that, it's exactly the same as what we had before. For example, it's very similar to the DQN that we looked at yesterday. Makes sense for everyone? Okay, makes sense. So the reason also, or maybe I should ask you a little exercise. Why does the IGM property hold here if you have this linear decomposition? Anyone want to try and explain? Anyone want to try and explain? Don't be shy. It's a good exercise to get everyone a bit more active. Or should I pick a volunteer again, see what's going on? So I'm going to pick volunteers. How about you? I'll pick you.
I'm really not sure. So maybe when we pick one action for one agent, we try to reduce. We have like on the right, we will remove all the Q values that are not for the action of the agent that we pick.
Mm-hmm.
And we have, I mean, we can take the max. Or...
Yeah, it's actually really quite simple. It's just a consequence of the linear decomposition. If we take the max for all of the individual components, basically by definition, this gives you already the IGM property. I think this is maybe a useful exercise to spend some more time on this in your free time when you have some time to go through exercises. For example, there will be matrix games, and we're going to be seeing how sometimes these linear decompositions work and sometimes not. And it's a useful exercise to just take some time and sort of massage these numbers, and you get a feel for what that means, decomposition. We're going to go through some examples, but yeah, I think you sort of have the right direction there. Okay, so let's look at value decomposition networks as the pseudocode. Okay, here's just a graphical depiction of what we're actually doing. This is the bigger joint action Q value that we're trying to decompose. And that's just defined as the linear sum. This is the plus sign here of the individual agent's components, okay? For agent 1 all the way to agent n. The sum of that gives you the joint action value. And this shows a graphical description of this linear decomposition that you just saw. In terms of the algorithms, it looks very similar to the DQN algorithm that you saw yesterday. Excuse me, you initialize the n utility networks. We use this term utility network to refer to the components of the agents because they're not actually value networks. So the individual components, the numbers that they return are not actually expected discounted returns. There are some abstract numbers. We just use the term utility in this case. Then there will be the target networks. You already know what that is from the description of DQN yesterday. And that's basically the parameters with the bar on top. And you remember how we're copying the original value networks into the target networks. And then we have the shared replay buffer D. We go through our episodes and time steps. We collect our observations from the agents, and then we do our epsilon greedy selection. Now here, this is important. Every agent gets to choose an action independently with probability epsilon either uniform random or otherwise they choose a greedy action with respect to their own component. So this is where this decomposition comes into play now. You see, this is the Q function, but using the agent i's theta parameters. So we're using this. Agent 1 uses this. Agent n uses only this. They're not using this bigger thing that we decomposed. They're only using their own decomposed component here. Okay? So that's important here. That's where this value decomposition comes into play. And that means the exact same greedy action selection we can also do after training because it only depends on agent i's history here. It's not using any of the centralized information. Then we apply the actions. We collect a shared reward. Remember, this is a common reward game, so there's only one scalar. And then the subsequent observations. We store these observation tuples into the replay buffer. And then we do our gradient computations, which means we sample a mini batch of experiences from the replay buffer. We do our label computations. If the successor state is terminal, then we know we only take the current reward. If it's not terminal, then we do our bootstrapping, very much like we've done before. And the bootstrapping, remember, is now defined with a TD target that has the sum here. Basically, we're taking the sum of these components. And for training, we can do this because during training, we have access to this information. After training, we don't need to do this sort of stuff anymore because we finished with the training. So we only need this. And this we can do after training with only the agent i's available information. Okay, we then compute the loss as the average over this batch. And then we do back propagation on the network and minimize this loss. And that's it. That's the whole pseudocode here. So the main thing is, I think the main thing to point out is really just this line here, line number 8, where it's seen that the greedy action really just relies on the agent i's component and only uses agent i's history. So it doesn't rely on the information of the other agents. Yes.
Sorry, maybe you mentioned it and I missed it. But what's actually the target that we're trying to learn here? Are we trying to maximize the social welfare or trying to learn the Nash equilibrium?
Oh, remember, this is actually now a common reward game.
Okay.
So there's only one collect reward. So in this case, it actually collapses to just maximizing the expected discounted return that everyone gets, which is the same for everyone.
Right.
So it's this question of Nash equilibrium and so on doesn't appear anymore.
Okay, thank you.
Okay. But good question. It's an important question. Okay. Right. So that was VDN. Now we're going to move into a slightly more complicated algorithm. Before I do that, though, I just wanted to check one more time. Any questions about VDN, or do you feel it's clear? Online question. Okay.
They were asking, in this pseudocode, where do we use the common centralized information? In updating the target or minimizing the loss function?
Yes, I think those things are the same. So here, in this case, where's the Z? All right, in this particular pseudocode, there's actually not a Z here. It's not implemented to use any specialized shared information here. In this case, the decomposition, the decomposed entities only use the local observation histories of the respective agents, and then for the original, yes, there's no special. The centralized component for the decentralized training with the decentralized execution. What's the privileged aspect here is that all the agents have access to all the other agents' decomposed components, which is everyone can see all of these other things during training, which they need to compute these these loss functions here. But after training, agent I or agent 1, for example, doesn't see anymore or doesn't even need anymore these components of the other agents. So I guess the answer to the question is the privileged aspect is that during training, they actually have access to the different individual agent components, which they need to compute these targets. But after training, so after the decentralized training, when they do the decentralized execution, they no longer need this kind of information. I think that's the answer. Okay. So this is the simplest possible thing you can do, I think, a linear decomposition. At least I'm not aware of an even simpler way to do this. Okay, so now let's look at a slightly more interesting or more slightly more general way to do this, because the linear decomposition is just that, linear. And as you know, linearization typically has various problems. For example, there's an implicit assumption that there is a convexity here, and convex polytopes might not always exist. So here we want to try and generalize this a little bit. A more general decomposition that also ensures this IGM property that we introduced can be formulated by assuming that the centralized action value function is strictly monotonically increasing function with respect to any individual utility function. So it sounds a little bit complicated, and maybe this part isn't quite so intuitive, but it's actually an interesting kind of property. What it means technically is that if you go for all the agents and all the joint actions, remember A is now a joint action, which includes the everyone's actions, then this bigger Q function for the joint action values, if you take the derivative with respect to the individual components of all the individual agents, then the rate at that point will always be strictly positive. That's what this property means, monotonically increasing. And I guess it's maybe not quite so intuitive really what that means. Probably would leave that to you in your free time to try and make sense of this. But basically, it's a property that theoretically ensures if you have a decomposition that ensures this, then you're able to achieve decompositions that are actually beyond linear. So the QMIX algorithm basically uses this. QMIX is probably one of the most famous multi-agent reinforcement learning algorithms. Certainly is the most famous algorithm in this category of algorithms, which does value decomposition. A lot of papers have built on this or used this as baselines. And in fact, we also found that empirically, it's a very robust algorithm. So the QMIX algorithm implements this assumption, which I'm showing up here, by using a mixing function fmix. This is actually a neural network as well that is learned, that aggregates individual utilities to approximate the centralized action value function. So it looks like this. This bigger Q function that we want to decompose is now a function of these individual utility functions for each of the n agents. But there's not a linear decomposition, which would just be the sum. Instead, we have a neural network that takes these components as input and then does some kind of nonlinear composition. So not necessarily linear, could be something else. And you know that neural networks are universal approximators that can represent any kind of nonlinear input-output relationship. So it gives us much more flexibility. Of course, this thing could actually decide to learn a linear decomposition, could well be the case, but it doesn't have to. It's not constrained to do that. So at the end here, this theta mix is just the set of neural network parameters that belong to this fmix function here. So QMIX, that's where this name is coming from. It mixes Q values, QMIX, and it mixes them using a neural network that is learning a certain decomposition, which is either linear or something even like more interesting than linear. So here's the architecture that basically shows this graphically. So here's the individual agent utility functions or decomposed components, which only rely on the agent's respective observation histories, history 1 for agent 1 and so on. And this is given into this mixing function, which has its own set of parameters. And in fact, there's also this hypernetwork, and I'll explain what that means. But basically, this mixing function takes as input these utility functions and then gives you, recomposes basically the value for the joint action. So the decentralized action value function is monotonic with respect to the individual utilities if all weights of this neural network fmix are actually positive. And that's an interesting sort of technical property. I'm not going to explain this in detail here, but basically, if you can do this, if these weights are positive, then you basically ensure this monotonic increasing property. So you just have to ensure that the weights are positive by obtaining parameters of the mixing function from a hypernetwork that is conditioned on some centralized information. That's where this is coming from. This is a sort of technical, like a technicality in this algorithm that is not particularly important for our lecture. It's basically an implementation way to ensure that there's these positive weights in the mixing function. And if we do have positive weights, we know that then this monotonic increasing property is actually satisfied. But it's not very important for us to focus much on this for the rest of the lecture. It's just a implementation detail, let's say. So really the important thing is actually just that part, I would say, conceptually speaking. Okay, and now we need to optimize this thing. So parameters of all utility functions and the hypernetwork are jointly optimized by minimizing this loss, which is again taken as the average of some kind of mini batch that you sample from a replay buffer. And basically, here are your experiences. In this case, there could also be other centralized information. And you sum over the experiences in your mini batch. B, uppercase B is the number of experiences, by computing this TD error or this TD update here. So there's the immediate reward in the experience, and then there's this discount factor, and you maximize over the join action in the decomposed join action function. Then these things are defined down here, and they're defined exactly using this fmix function. Okay, so first starting with this part here. In our bootstrap target, this is just defined as composed by this mixing function using the individual utility functions of the agents. And then the maximizer of that, which is used here, is actually similarly defined by taking the fmixing function, but now taking the maxes of the individual agent utility functions. Okay, so the max moves inside here, basically. Okay, so now let's look at some matrix games, make it a little bit more tangible to see what's actually going on. And this is interesting. So to better understand how these value decompositions work in practice, let's look at some example matrix games. Here is a linear game. Linear game, we just call it that because it's linearly decomposable. There's only two actions, A, B, and there's some numbers we made up. And there's a monotonic game. We call it that because it's not linearly decomposable, as you just see, but it's can be decomposed with an algorithm like QMIX that has this monotonic assumption. And then there's a climbing game, which is a little bit more complicated. And it turns out this can actually not be decomposed by either of these two algorithms. And you need something a bit more general. And in the literature, there are more general algorithms. There's algorithms like QPlex and others, which are going beyond QMIX in terms of their representational capacity. But we're not talking about them here in the lecture. So that's what I just mentioned. The linear game is linearly decomposable. Monotonic game only with something like QMIX. Climbing game is not decomposable by any of these two. Let's look at some results. So this is the matrix, reward matrix for this linear game that I showed you, the first one. And first, let's look at the VDN decomposition in the center here. Okay, what we want to show in this is that the decomposition when you recompose the join action values, for example, with the linear sum, you reconstruct exactly these values. You reconstruct exactly the values in the cells here. That's what we want to do with our decomposition. And that's basically what we're seeing here. So this is how a VDN decomposes these numbers. Basically, what you see here now replacing the action labels is actually for each of the two agents. There's two agents. They have their individual utility functions, and it shows the numbers that these utility functions return. So for agent 1 on the rows, you see that for action A, it gives it the utility of 0.88. And for agent 2, its utility function for action A gives it a utility of 0.12. So if we take the linear sum of these, you know that you have the sum of that is exactly 1. Or if you look at what the utility functions output for actions B, it gives this number for agent 1 and this number for agent 2, and the sum of that is exactly 9. So you can see it's sort of beautifully decomposed. The linear decomposition worked exactly here. And now the agents can go ahead and use only their decomposed parts of this function. For example, agent 1 only uses its rows here. And if it takes the maximizer individually, which would be action B, and the same is done by agent 2 using the maximizer here, then we know that this join action here, even though they chose this independently using only their own utility functions, the join action of that is also a greedy join action as according to the original function. So that's exactly this IGM property that we wanted. If we look at the QMIX decomposition, which uses this nonlinear fmixing network, it sees that you can see that it also learned this decomposition, but it has very different values. These are not linear values at all. It's something else. And in fact, what I'm not showing here is actually what this F-mixing does. And I don't know, because it's a neural network and it's hard to extract the logic here, but it's a nonlinear composition basically. And it turns out that if you apply F-mix to these two numbers here, then the F-mix function returns exactly 1. If you apply F-mix to these two numbers here, it gives you exactly 9. I just don't know what this F-mixing does because it's a complicated neural network. Okay, we can make several observations from this. First of all, VDN and QMIX are both able to learn the decomposition here. The learned decompositions are not unique. The VDN decomposes it like this, and F-mix has a very different decomposition. I don't know what it's doing. And the individual utility functions, in particular for QMIX, can be difficult to interpret. That's what I just said. If you look at the numbers here, it's not quite clear how this F-mixing is putting them back together. So that's maybe not so nice about it. Let's look at the next game. This is now the monotonic game. The matrix rewards are shown on the left here, so 0, 0, 0, and then only for a BB they get 10. So let's look at the VDN decomposition. In this case, you can see it's actually failed to learn a decomposition. For example, the utility functions for agent 1 and agent 2, if you take the sum of those utilities, then you get some weird numbers. 7.53 is not 10. And here you get something that should be 0, but it's not 0 on these numbers. It's just not possible theoretically to actually decompose this linearly. So it's a hard restriction in the algorithm. It's not capable to deal with this. QMIX, on the other end, is able to decompose this, and it's because this kind of game does have this monotonic increasing property that I explained earlier. So in this case, you see again the values of the individual utility functions from the agents, and there's some magic going on with the F-mixing network, and it produces exactly the correct numbers when they recompose the numbers. But again, I don't know exactly what the nonlinearities are and what the internal logic is of this F-mixing. It's a neural network, and it's learned this on its own. You can actually show this graphically. So this is a 3D plot where basically we're showing the decomposed elements of these two agents here with the utility functions basically. And you see that the F-mixing is exactly basically reproducing what the original reward matrix showed. Only QMIX is able to represent the nonlinear but not monotonic relationship between the individual utility functions. So it's interesting, and you can easily create a script like this yourself in Python, where you can then run this decomposition with QMIX for all kinds of matrix games, and you see sort of what the landscape is and what it's doing. And there's actually an exercise for today after the lecture, which is when you use QMIX, and then you get to use this implementation. You can play with matrix games, and you can see what's happening. And lastly, let's look at this third matrix game, the climbing game. This game is not decomposable by either of these two algorithms. So in the climbing game, neither VDN nor QMIX are able to learn the true centralized action value function, and they converge to suboptimal policies. Okay, so let's see what's going on. VDN is doing something completely off the mark. You see it's produced some utilities, but if they linearly summed up again, it gives you some weird numbers. For example, this should be positive 11, but it gives you negative 8. This should be positive 5, but it gives you 8.59, which, yeah, it doesn't make sense. It's not linearly decomposable. QMIX also fails here. It's because this game is not doesn't have this monotonic property. So it's actually not able to learn a value, an F-mixing network that actually recomposes the joint action values correctly. So you see, again, negative 11, it should be positive 11. I guess the 5 is basically correct here. This should be 0, but it's almost negative 5. So it's not able to decompose this. And so if in that case, you need to look beyond QMIX, and there's more sophisticated or more, I guess, general algorithms that actually are able to learn these kinds of decompositions. Some of them we describe in the book as well. Okay, now let's look at something more interesting than matrix games. Matrix games are useful because you can write them down, you can see the numbers, you can understand what's going on, but they're maybe not exactly what we want to solve in real games. So now let's compare independent DQN, which we introduced yesterday, and VDN, which is the linear decomposition, and QMIX, which is the nonlinear decomposition. And let's look at a common reward level-based foraging game where there are two agents, both level 2, and they need to collect these 3 apples. remember, they can all collect the level 1 apples independently because their levels are high enough. But for the apple with the level 3, they have to work together to sum their levels, basically. And it's a common reward game, meaning that if any apple is picked up by any of the agents, they both get the same positive reward. So here are the results. On the x-axis, you have your training time steps. On the y-axis, you have your return. There's 3 algorithms. Blue line is independent Q-learning, orange is VDN, and green line is QMIX. And you see that independent Q-learning is struggling to learn this. It's a large state space. Then there's the VDN is doing better already, and then QMIX is doing much better than these other algorithms. It's actually learned this quite nicely. It's almost close to optimal, which is 1. The best you can do is 1 in this game. So it's a nice little visualization of how these algorithms are, the differences in the performance of these algorithms. So this is the end of the first part for the deep multi-agent RL algorithms. As a summary, we started by talking about training and execution modes in the decentralized training or centralized training, and then also decentralized execution. We looked at independent learning with deep reinforcement learning, something like independent DQN. The idea just being that every agent uses its own copy of a single agent deep RL algorithm. Then we looked at multi-agent policy gradient algorithms, which is this idea that we have policy gradients, but we make it multi-agent by sharing certain information between the agents. And then just now we looked at value decomposition approaches for common reward games, where we looked at the linear and nonlinear decomposition and so on. And so we're going to go into the second part here when we're talking about some other ideas and techniques, agent modeling, parameter sharing, and so on, policy self-play for zero-sum games and so on. We'll see how far we can get there. But before we make that move, let's see if there's any more questions about the value decomposition approaches. Any more questions?
So in some of the matrix games, you said that VDN cannot be applied. Is that because of the 0 values that is in the matrix?
Yeah, that in that case, it was because of the 0 values.
Okay, in that case, can we add a kind of a small epsilon to these values, like a very small value, and then apply the VDN instead of?
Yeah, I guess you could play around with the game to make it compatible again. The point of this was just to show you when it does not work, basically. But you may not always be able to do this sort of modification, right? And yeah, you maybe don't want to, right? It's kind of annoying if you have to do something like that just to make it work, right? And in addition, it might also change the nature of the optimal policy, which is also something you may not want to affect. So you could do this, but probably not desirable.
Okay. And one more question. So this IGM property holds only for the common reward games, right? Or can it also hold for?
These algorithms are all designed for common reward settings. I guess we haven't thought so much about how to generalize this to non-common reward games. So I think I don't have a strong answer to this at the moment. Probably would be something to think more about how to generalize this.
So at the moment, for the non-common reward games, we use the policy optimization.
Yeah, the other algorithms. Okay. These value decomposition algorithms are not defined for these kinds of games.
Okay, thank you.
More questions here?
Thank you. So I had a question about both parts. Could we use mixing networks and value decomposition for the critics in the policy gradient algorithm in order to reduce the complexity of the critic that actually, instead of having, I don't know, an action space to the power of the number of agents, would have an action space and a more manageable action space.
Yeah. So there are papers I'm aware of where they have tried this kind of combination, but I don't actually recall what their findings were in terms of what works and what doesn't, to be honest. And I also don't know if these things were ever published. I think I saw some things dumped on archive, basically. So I might be able to dig that up again and could possibly send that to you if I can find that again. And I think we once had a master's student a couple of years ago who did this kind of project. And I don't remember anymore what he found. I need to find that again, and I could maybe share that with you. But basically, that was exactly the idea that he explored. Yeah, sorry, I don't recall the results there, but technically it's possible. You can do this kind of thing. Yeah. Probably worth studying more as well. More questions? Anything online? Okay, good. Then I think let's move into the next part. We're going to just do a little bit in the next part, and then we'll go into our mid-break. Okay, so part 2. Let's see what we can do here. Okay, first of all, this reminder, this is the book. Please make sure you check it out. Okay, there's a few topics here to cover. Quite a few interesting ideas. Agent modeling is something that's very important in multi-agent systems and interaction in general, but also you can use this in multi-agent reinforcement learning. And it's something that's very close to my sort of thinking because I used to do a lot of work in this kind of space. Parameter and experience sharing is a very important technique to scale multi-agent reinforcement learning, make it more efficient. This is something that a lot of people do in practice just to make it more efficient. And then there's some really advanced techniques, policy self-play and zero-sum games. Some of you may have seen these algorithms by DeepMind where they beat the human world champion in Go and use exactly these kinds of techniques. And population-based training is also important type of research. This is actually, for example, the StarCraft II game that I showed you where DeepMind and also others developed these algorithms that could beat professional players. Also used population-based training here. So let's see how far we can get. Going into multi-agent modeling, first of all. Okay, in multi-agent RL, agents need to consider the policies of other agents to coordinate their actions. I mean, I guess strictly speaking, they don't have to, but it's a very good idea in order to get some benefits. An approach is presented so far account for the action selection of other agents only indirectly. So either via the distribution of the training data, which depends on the policies of all the agents. This is exactly what happens in independent learning. So I don't actually exactly model that you exist and that you choose actions, but I do get to see a training distribution which is affected by your actions, even if I don't even know that you exist. So indirectly, I get to see something that tells me something about the distribution of your actions. And also training centralized critics, for example, that we condition on the actions of the other agents, that basically also means that there is a component in these multi-agent policy gradient algorithms where we consider the action selection of other agents. And so we need to sample from their policies. But now the idea is, can we provide agents with more explicit information about the policies of other agents so they can coordinate better? So agent modeling is all about reasoning and modeling and predicting how you think, how you choose actions, how you behave, basically. Okay, so here's a reminder. It's actually not really a reminder because we skipped over this, but if you read the whole book, it's a reminder, basically. In chapter 6, which we skipped, this is the first time when we talk about agent modeling. And basically what it means is you want to learn a model of the other agents to predict their actions. This is the most basic type of agent modeling, and it's also called policy reconstruction because I'm trying to reconstruct what your actual policy is based on what you've done in the past. And then once I have an estimate of what your policy is, a model of you, I can compute a best response against you, against your model. Remember, best response means it's the policy that maximizes my return, assuming that you have a specific model. Graphically, it looks like this, an agent model. You can basically, write it like this. There's some kind of model, a neural network, for example, or something else. It takes as input observations, for example, the history of past states and the history of past join actions. There's some internal computation going on, and then you get a prediction. For example, you want to predict the probabilities of the actions of that agent that I just modeled. But there's a lot of other things you may also want to predict. For example, in self-driving, we've done a lot of work about goal recognition, which is when I want to predict what your longer-term intentions are. What do you actually want to do in the long term based on what you've done in the past? Not just the immediate action. What do you want to do in the long term? Or also beliefs. For example, theory of mind. I may want to have a model that tells me something about your state of mind. What do you think is the state of the world? And then I can say things like, what do you think that I think that you want to do? What do I think that you think is the state of the world? So it's very important to do this kind of reasoning, especially for humans. Humans do a lot of this recursive reasoning. And there's a huge amount of literature. And so if you want to check out this kind of work, then I would point you to a survey that I wrote a few years ago with Peter Stone, which was published in the AI journal. And this gives you a really comprehensive description of the different methodologies for agent modeling to get started. Okay, so but basically we only do one type of agent modeling, which is policy reconstruction. The idea that I want to predict exactly the probabilities of reactions for the next time step, basically. So in chapter 6, which we skipped in this week, but which is in the book, we model the other agents' policies as stationary distributions. And basically we just compute the average action frequencies. So I've seen that in the past, you took a certain number of actions, and I just average basically these frequencies, and that's going to be my model of you. It's very simple, probably one of the simple things you can do. But the problem with this, action counting and taking the frequencies is that this tabular agent modeling, where you have these exact sort of frequencies you store for the different states, they're limited because you're not able to generalize to a very, very large state space, for example, with billions or millions or billions of states. You won't be able to calculate the action frequencies in all these states. You need something that's really that's able to generalize. And that's where neural networks come back in. We can use neural network and deep learning to actually represent these agent models. Before deep learning, people used other kinds of models to represent the agent models. For example, decision trees were very common, or finite state machines, or logical descriptions. You can do all kinds of representations to describe how you behave. Neural networks are just a very convenient, more modern way of doing this now. Okay, so here's a reminder of how we did this previously in chapter 6 in the book. So first, this is an algorithm, joint action learning with agent models, or JAL-AM. Basically, this is an algorithm that uses Q tables to find over joint actions, and it uses these agent models that we're learning, these action frequencies, to compute to marginalize the actions of other agents away, and then we can use a maximizer for our own agent. I'll explain what this means in a second. First of all, agents learn models of other agents J conditioned on the states. So this pi hat here, pi minus I hat, this is our model now. We use this hat notation to describe the model for the policy of the other agent. And it gives us a prediction of the probability with which that other agent will actually pick that particular action in that particular state. Okay? So it looks exactly the same as what the policy would do, but this is now our model of that agent minus I. So we have this hat notation here. Agents learn value functions defined on the joint action. So this every agent I has this joint action Q table for each state in joint action. And then using this value function here and the agent models up here, we basically compute the action values available to agent I for the different actions available. So AVs for action value. This is the state, these are the actions available to agent I. And basically it works like this. Because we do not control the other agent's actions, we need to marginalize them out. So that's what we're doing here in the sum. We're summing over all the possible actions that the other agents could be taking. And then we combine that with our action that we want to evaluate here to make a joint action. And then we take the Q value from the table that we learned. And we need to also weight that by the probability with which our model tells us that the other agents would actually take these particular actions that we just summed over here. So that's what this factored probability is. Okay, our agent models feature here. They give us the probability with which the other agents will choose certain actions. And we use that to sum over the possible actions of the other agents and weight by this probability. And this sum here basically gives us an exact definition of the expected or the average action value for our particular actions that we can actually choose. And then once we have this here, we can basically do the standard Q-learning approach. We can take the maximizer of this to choose our own action, and we can take the maximizer of this when we compute the bootstrapped value for the update targets. Okay, is there a question here? Question there? Yeah.
Sorry, I'm not sure I'm following the notation in the first line when you are referring to the actions of the other agents. Are you meaning there in the first line? Yeah. Are you meaning there all joint actions of all the J agents, or do you mean just one action? Because here in the last line,
I see the confusion.
minus I corresponds to every single other agent, no?
Yeah, yeah.
But here in the displays.
Yeah,
So is this notation?
I think I need to remove the J here. So basically, remember -I, the notation just means all the other agents except I, which is ours. So basically, it's just a convenient way to say if there's more than 2 agents, then -I is all the other guys. But this could just be J if it's just one other agent. And in fact, you would normally have independent models for the other agents. So would be like if I'm agent 1, then I'd have a model for agent 2, 3, 4, and 5.
Okay, that was my question. If it was like independent for every single other agent.
Yep.
Okay.
And they are independent because that's why we have this factorization of the joint probability here. And the reason why there's J here is because when we take the joint action for all the other agents except agent I, then we still want to be able to access the individual actions of the other agents, and that's why we use J for. But yeah, I agree. You're right. I should remove this J here, which I'm going to make a note about that.
Thanks.
Slide 6, remove J. Okay. So that's a tabular simple algorithm that uses something very similar to Q-learning, but it actually uses joint action Q tables, and it uses these agent models of the other agents. The reason why I've just introduced this is because this is probably the simplest thing you can do, and we want to do something just like that, but with these deep learning-based algorithms and models. So, okay, so we use these action values to select optimal actions and also for Q-learning updates. So the question now is, how do we do something like this, but with the deep learning algorithms and for partially observable stochastic environments, which is when we don't actually have access to the states, which is what we just assumed. So first of all, we represent all the models of the other agents as a neural network. So now there's these parameters phi. Remember, phi we use as the parameters for policies. And this is a model. That's why we have this hat notation here. This is the model for agent J, which uses these sets of parameters. And it's now conditioned on agent I's history because that's what we have access to. I don't have access to this guy's history. I only have access to my history, and that I need to condition on that. Given the observation history of the agent I, which is this HI, the model for this other agent J outputs a probability distribution over J's actions. Okay, so just like the policy for agent J. And we can train this thing basically using a direct cross-entropy loss minimization. So it looks like this. Here's this loss function for over the parameters of the agent model for agent J. This is I's model for agent J. This is what this notation means. And basically, we observe a sequence of actions from this other agent J, and we just want to minimize this expression, which basically means that we maximize the probability with which we predict these actions of the other agent. Okay. So remember, the probabilities are between 0 and 1. So if we take the logarithm, which is differentiable, we end up with numbers between infinity and 0. And that's where we take the negative sign so that we basically have a positive expression. And then if we minimize this, it means we push up the probability that the policy predicts this particular action. So you can just take a minute yourself to parse this expression, but it's straightforward. Okay, and then agent I can compute its expected action values just as we've done before. This is the same expression. We marginalize over the actions of the other agent. We construct the joint action by combining their actions with our action that we want to evaluate. And then we also weight that by the factored joint probability that our models give us for these actions of these other agents. Okay, there's another issue with this, which is that if we want to compute this action value, then we need to sum over the actions of the other agents. This is what we just saw down here. And that might not be very desirable if there's a lot of agents or if there's a lot of actions. So we need to deal with this in some way. Yes?
So now, suppose we have n agent. Does it mean we have n squared networks now? Because for each agent, you have its own policy plus the policies, the estimated policies of all other agents.
Yes. Yeah.
So we would have n squared networks right now.
But you don't actually have access to the real policies. So you only have n models. Okay. For each of the other agents, I have respectively one model, basically.
Yeah, but what I understood that previously in the previous topics, we were like kind of training all the agents
Oh,
in a
yeah.
simulation. So if you now do a simulation with all the agents, you would need n squared networks in your entire simulation.
The n squared, I guess, comes in when you say that every agent has n models for
Exactly.
the other guys.
Yes.
And so then it's n squared, yes, collectively, basically. But individually, they only have their n models, or actually n minus
Yeah,
one.
yeah,
basically.
exactly. Yeah, that's what I mean. So, but my point is that, so we are simulating all the agents.
In the training,
this-
yes, they have
yeah,
their
yeah.
policies. Yes.
Okay, sure. Okay,
Yeah.
thanks.
Okay, so in order to address this problem that we have to sum up over all the possible actions for the other agents, we can do a straightforward thing, which is to approximate this action value by just sampling k actions from the models that we learned for them. So we sample k actions, and then we just take the average sum of the joint action values here. This expression just means that these actions of the other agents that we sample averaging over, the k from 1 to upper k, they're sampled from the models that we learned from these other agents. So it's a sampling-based way to approximate this full sum that you saw earlier. Simple way to address that. Okay, let's look at some results. Here's level-based foraging. There's two agents, one with level 1, one with level 2. And in both of these cases, they actually have to work together because the apples have a high level that requires that they always work together. And the results look like this for 3 different algorithms. This is independent DQN, which we introduced yesterday. The blue line, you can see it's not doing anything. It's actually failing to learn altogether in this environment. And then there's these 2 other lines, which is joint action learning using deep learning approach. One is the orange line, which uses the exact sum, the complete sum. And then there's the approximation with where we sample k joint actions. And if you're actually asking why it turns out that the green line is better, which is maybe a little bit counterintuitive, in the book, we give a few different hypotheses for why that is, but we didn't end up analyzing this fully. We think that the stochastic nature of the sampling approach actually improves the exploration ability, basically. But the main thing to take away is that the agent model really helps the algorithms to solve this problem. They're reasoning about the actions of the other agents, and that helps them to solve this problem that they need to cooperate, basically. Independent DQN doesn't do any of this, and it's actually failing to learn that they need to cooperate in both of these instances here. You can also see that we're pretty close to solving this optimally. Again, number 1 is the best you can do, and in terms of average expected return, we are pretty close now already. Okay. Yes?
The agent models here would be learned from the observations of the other agents. So
yes, during centralized training, we know what actions they chose, basically.
okay, and is that a big? So we're doing centralized training and decentralized execution with the agent modeling.
Yes.
Okay.
During centralized training, we know what everyone's actions are, so we can use them as the targets for our neural network models. But the models that make those predictions, they're actually conditioned only on my history. And so after training, I can still query these models with only my history, basically. But during training, I was able to give them the actual labels, which they only needed during training. Do you feel that makes sense? Okay, if not, I can go back to the pseudocode if you would like, or we can talk more later. Okay. So now what we've done so far is we learned these explicit agent models. Okay, I have one neural network for agents, this other agent, and another neural network for this other agent, and it gives me explicit probabilities to predict these agents' next actions. And that's one way of doing this, but it has certain limitations. And there's other ways of doing agent modeling. One idea is that we actually want to not have to use these agent models to compute explicit best responses because it can be kind of complicated and expensive to do this. Instead, I want to have a compact representation of this other agent that encodes certain information to characterize that agent. And then I want to be able to condition on that compact representation in my policies and in my value functions. It's a different approach to agent modeling. Let's see how that works. Can we integrate agent models into multi-agent policy gradient algorithms by conditioning policies on these agent models? We need a different kind of representation, not these explicit neural networks. To condition policies and value functions of agents on the policies of other agents, we need a compact representation. That's what we're trying to do. And basically, the way we're doing this is now to learn embedding functions, which is basically a way to compress another agent, or what another agent has done so far, into a fixed length vector. And we can condition a policy on that fixed length vector, basically as an additional piece of information. Let's see how that works. Okay, here's a general framework that you can instantiate in many different ways. We just had a master's student finish a nice piece of work where he took this framework and he evaluated it in all kinds of instantiations, and we described this in the book as well. So basically, agent I, every agent is doing this, but let's look from the perspective of agent I, trains an encoder-decoder architecture. This now gets into the deep learning background. If you don't have this background, it's not a problem. We can still explain what this means. So first, there's an encoder. This is a function FE, which has parameters psi here. And what it does is given an observation history for that particular agent I that is doing the modeling, so my history basically, then output a compact representation M. This is just a vector of scalars of the policy of that other agent. Okay, so M is an embedding. It's an abstract vector base. It's a vector of these abstract scalars, and these numbers in the vector, they're supposed to encode certain information that characterize that other agent that I'm modeling. And then these embeddings need to be trained to mean something useful. And for that, we use a decoder. The decoder FD, on the other hand, it takes as input this compact representation M, and it's learning to predict, based on this compact representation, to predict the policy of that other agent. So technically, it means to predict the actions of that policy of that other agent. Okay. Can I ask who here is familiar with autoencoders or encoding and decoding architectures? Hands up. I think quite a few people, about half. So it's exactly applied here. But for those of you who are not familiar with this, it's basically a compression technique. Imagine you have one neural network, which is the encoder, and it takes as input, for example, the sequence of all the past things that happened, the history, everything that's happened in the past, takes it as input. And then it compresses that into a vector of numbers. Okay, it encodes this information that it's gotten into a vector of numbers. That is the thing that we can now take and put into our policy to condition our policy. But in order to train meaningful numbers that actually sort of give us something useful, we add this decoder network. Only during training is after that, which takes this embedding and is learning to predict the actual, or to reconstruct the actual actions from that particular agent that we're modeling that was coming into the input in the first place, basically. And that's why implicitly the neural network, the encoder, will learn to encode in such a way so that the decoder can actually reconstruct the actions of the other agents. It's a deep learning kind of approach, which is really kind of beautiful if you think about it. So you leave it to the network to actually compress it in some meaningful way. And visually it looks like this. Here's our encoding network. It takes as input the agent I's history and has its own parameters psi, gives the embedding. The embedding is the thing that we care about. And that is used then to condition our policy. This is our policy pi. We condition that to choose some actions. And the embedding itself is trained by putting it into a decoder, which then uses the embedding to try and predict the actual policy of this other agent. So the actual actions of that other agent. Does that make sense for people? If not, we can talk more. The question there?
So the output of the decoder, is it the policy of the other agent, or
It would be the actions.
Okay.
The actions of that. It's just a sort of a convenient way to say we're predicting the actions of that policy.
Okay.
So just a bit like intuitive. I cannot it's not very intuitive. Why would the history of agent, like my history, would encode a function for another agent? So this
Yes.
is a bit
Yes.
intuitive. Yes.
Yeah, it's interesting, right? First of all, we need to understand why we're doing this. The reason why we have to do this is because after this training, I don't actually have access to your history, right? I can only use my history to make predictions about who you are or about what you're doing. And my history hopefully will contain some kind of information that relates to you. So in the ideal case, my history includes your past actions. And then that's kind of straightforward, I guess. If my history includes the past states or like some pretty informative observations and also your past actions, hopefully that's like a rich piece of information to make predictions. But on the other hand, if my own history with my own observations does not include your past actions and is very limited observability and really doesn't say much about you, then this kind of approach is not going to work well. So an approach like this has to assume that whatever I get to observe in the environment includes some kind of signals that relate to who you are or relate to what you've done in the past. There's also other indirect ways, so it's actually quite clever. For example, if my observation history only includes information about how the states of the environment evolves over time, but not at all about your actions, implicitly between these state changes, it can actually learn to derive what your actions must have been between these state changes, if your actions were really important to these state changes. And even implicitly in that sense, the model can actually capture information about what you're doing, if it's important to the state changes. So there's quite a bit of sort of dark magic, deep learning magic going on. But at the end of the day, it really depends on how rich your observation history is. And the whole thing is not going to work if my own history has very little sort of implicit information to talk about you, basically. Yeah, so you need to be aware of that, basically. But then on the other hand, I mean, to be honest, if that is the situation in the first place, then you shouldn't even consider agent modeling. It doesn't make sense in the first place then, right? Because if my history doesn't include anything about you, probably not a good idea to try and use that. Okay. More questions?
One online. Given the main input here is the history, why is this different to simply expanding the parameter size of phi?
Sorry, I didn't understand. Say again.
Given the main input here is the history, why is this different to simply expanding the parameter size of phi?
To simply expanding the parameter size. You mean those 5 parameters that go into our policy? Yeah, I'm not sure I understand the question, to be honest.
Not my question.
Yeah, I'm sorry. Maybe the person who asked the question can elaborate a little bit more later. I think I don't understand the question, to be honest. Okay, let's get move on then. So agent I can condition its policy on the compact representations M that we learned here. And by the way, this approach we actually first proposed in a NeurIPS paper that came out in 2021 or so. And there we described like a whole general sort of framework that does this. And you can go back to this NeurIPS paper. It actually relates to what we just talked about. The whole motivation in that NeurIPS paper was this idea that we want to do agent modeling or opponent modeling when we only have access to our own local observation. And we talk a lot about, what we just talked about here, when it works and when it doesn't work, and what kind of information you need to have in your history. Okay, so moving on. So the encoder and the decoder are jointly trained to minimize this cross-entropy loss that we see here. And this basically just means we want to learn an embedding that predicts with a high probability the actions of the other agent that we're modeling using this cross-entropy loss that we just saw earlier as well. And now this model, pi hat, is actually defined with this encoder and decoder combination. The encoder takes our history, its own parameters, gives, say, an embedding. The embedding itself is fed into the decoder with its own parameters, and that's supposed to then basically represent this policy that we use here in the cross-entropy loss. And so we can train this end-to-end, basically, with one big backpropagation move. So the encoder and the decoder agent models can be integrated into multi-agent reinforcement learning by conditioning the value functions and the policies on the obtained policy representations. The embedding that we learn is simply a vector of scalars, and that's a perfect representation to feed as input into a neural network input layer, in addition to any other information you want to feed in there. Let's look at some results. So this is level-based foraging again. This is now an example where there's 2 agents, and they also have to always collaborate. So because the level of the apple is 3, which means they always have to work together. Here's some results for 2 algorithms. The blue line is centralized A2C, advantage actor critic that uses the state during the centralized training. And then we have the orange line, which is the centralized Actor-A2C algorithm, the same algorithm, but it actually also uses the embedding for the agent modeling that we've just introduced. And you can see there's a huge difference in the performance. Now we're much closer to optimal performance, and here we were really not doing so well at all. And also you can see that we're plateauing off here already. So it's not like the blue line would, it doesn't look like the blue line would actually catch up here. So agent modeling, as we've seen before, makes a big difference in terms of the ability to solve these kinds of tasks. You can generalize this. I mentioned this earlier. You can actually have different kinds of information you want to predict. For example, in the algorithm that we just evaluated, the decoder used the embedding to reconstruct the actions of the other agent. This was basically what we were trying to learn here, but we can actually try to reconstruct other things as well. For example, we can try to reconstruct also the observations of these other modeled agents, because during training, we assume that we have access to their observations. So this is privileged centralized training. We can even try to model what their rewards must have been. And the idea is that if we have access to this kind of rich information during training, then hopefully this gives you lots of signals they can use to learn even more informative agent models. So this is a very general framework that can be instantiated in a number of different ways. And I mentioned that we had this master's student who did the master's dissertation with exactly this framework, and he tried all kinds of things here in the red box. And you can actually find this dissertation if you go to our research group website, you go to the blogs, and on the blog page, there's a blog post about master's dissertations. And the most recent dissertation that's listed on that blog post is his dissertation, so you can find what he did there. Okay, that's now agent modeling. And I think maybe now might be a good time to do a break. But before I do that, just wanted to see, is there any more questions about agent modeling? Online questions, or there's a question here?
Yeah, so I think it's similar to what the online question was. So basically, what is the advantage of using the encoder-decoder over a big neural network? Because in autoencoders, we use the latent space to gain some insights. So do we get something from the comparative representations here? Or...
Yes, I mean, they're trained in a different way, right? The embedding is trained to reconstruct information about the other agents. So they will be informative. I mean, we expect that they will be informative if our observations include some information, and also if we use the right kinds of targets, like reconstructing their actions. But if we just make our own policy bigger, I guess that was the question. Okay, now I understand. If we just make our own policy bigger, that doesn't mean that the policy is then trained to actually represent anything meaningful about the other agents. So for example, during training, even if the network is bigger, if we train that, there's no explicit labeling in the targets that represents information about the other agent, right? So it wouldn't, because of that, it wouldn't necessarily happen that we learn these kinds of models. I guess I understand the question now, and that will be the answer.
Thank
you. Question there?
So could you use this kind of agent modeling for a competitive zero-sum game, such as poker, for instance, that you would like to model what kind of player are you against, and you want to use that information to condition the policy? Would you do that kind of thing, or?
Yeah, for sure. For especially for competitive environments, I think it's very important to have these agent models, because you need to make inferences about these other agents' intentions, strategies, or what their next, the next actions are going to be. In poker, there has been work where they're trying to do agent modeling, but it turns out that in poker, it's already very strong if you just learn a minimax policy, which does not require opponent modeling. Because if you remember from the 2 days ago when we introduced solution concepts, including minimax, minimax means that it's a solution where every agent's policy is optimized against the worst case opponent. So that would be the agent model. It's a model implicitly that tries to destroy us as hard as possible, right? Optimally destroy us. And if we have our own policy that is optimized against this worst case situation, then for a real poker game, that's kind of a good approximation, because they tend to be really professional, right? So then like the state-of-the-art approaches for poker, they tend to rely a lot on computing profiles that are like that, designed like that against worst case opponents. But there is research for poker as well, where they actually integrate explicit opponent modeling features as well. If we move away from poker, then I think in general, it's just important to understand your opponent. You need to understand what this opponent's weak spots are, right? That you want to then exploit. It's not a good idea in general to optimize simply against the worst case opponent, because that also reduces the optimality of what you can achieve. If you always assume that there's like a completely like a worst case opponent, in reality, your opponents will have certain weaknesses. They will have certain limitations. And you want to have a policy that's able to understand and exploit those limitations. And that typically requires something like agent modeling to understand that. And then you can hopefully do even better.
Thanks.
Okay.
So in the encoder-decoder training, so encoder and decoder are trained jointly. And is there any advantage that we take a policy which is already learned and then train the encoder-decoder, or both the policy and the encoder and decoder are trained jointly? So is one better than the other?
Okay. Yeah, and just make sure I understand what you're saying. So you're asking, is there basically a difference or a benefit to, so the decoder and the encoder, they are jointly trained because the backpropagation goes through them. But you're saying, what about jointly training those two components also with our policy?
Yeah.
Is that what you're asking?
Yeah.
Yeah, so we did both of these approaches. In fact, the first approach was actually jointly with the policy and the encoder and the decoder.
Mm.
But the bigger you make the pipelines for your backpropagation, the more difficult it becomes to actually learn, because you have effects in your deep learning, for example, vanishing gradients, right? They tend to vanish if you have long pipelines, basically, and it becomes difficult to extract signals. So I think after this first approach, we decided to move into a decoupled approach where we train the encoder and decoder separately from the policy.
Mhm.
And that worked just more stably for us, because then we don't have these deep learning specific problems with the vanishing gradients and other effects. So I think the most recent iteration that we ended up doing, and I think that we also put in the book, is when those two things are trained separately. But the encoder and the decoder, they are trained in one pipeline with one backprop.
Okay. And a single decoder is used for all the other agents, right? Or
What do we do? So you can have a single encoder that takes the history and an agent number for the opponent that you want to predict for. And you can train that, yes, basically one encoder to actually give you an output for the other guys. But you need to have some way to reference who you want to actually make predictions for, right? So you can give it like this agent ID input. But I think probably the cleaner way would just be to have separate models or separate encoders for the other agents. And there's also another way to do this. I think what we did is we actually learned a big joint opponent model that actually learns not just to reconstruct agents, this one particular agent's actions, but actually to reconstruct the joint action of the other agents. And then you also make, like you have one shared embedding that is informative for all the other agents. And then you don't have to worry about this thing anymore, that you have separate models for the separate other agents. And it goes back to the question that we had earlier here, when you asked about the n-squared models and so on. With this kind of approach, then there's only just one model always. Yeah, like a joint big agent model. So I guess the takeaways from this answer is that there's some flexibility. You can be creative with how you shape this.
Thank you.
Okay, I have a few. I will select some of them.
Okay.
I'm saying I'm working on UAV swarm trajectory design. So if my reward is always negative, then what should be the issue?
You're working on what? UAV trajectory design.
Yeah, swarm trajectory design.
And so you have a cost. If the reward's always negative, you have a cost, I guess. Not sure I understand what the question is. So you want to still maximize your objective, right? Because you want to minimize the cost. What is the question? I'm not sure I understand what the question is.
Like I have the following test.
Yeah.
Don't have any contest.
Okay. Yeah, sorry, but repeat again, maybe.
I'm working on UAV swarm trajectory design. So if my reward is always negative, then what should be the issue?
Then what should be the issue? I don't know. It's kind of an ill-defined question. I don't know.
Okay,
Next question.
I go to another one. Which encoder-decoder architectures are usually used for embedded training?
Which encoding, decoding architectures? Okay, I mean, the most basic thing you can do is just standard feed-forward networks, but they can be problematic if it's important to make inferences over histories of observations if there's partial observability. And you don't want to do things like super long input layers. So we actually ended up doing recurrent encoders that have a recurrent input layer, so you can feed your observations as they come in, and then there's an internal mechanism that gets updated. But the decoder is just a feed-forward network again to keep it simple, because it's harder to train recurrent networks. So those are two examples, of how you can configure this. You could go even more crazy. You could probably have a transformer-based model to represent, your whole encoder. It's not something that we tried, but you can try these kinds of other techniques as well.
The last one. Right. In terms of not learning information about other agents, if the policy network is made bigger, would that not just imply that knowledge on other agent actions is less important?
So I guess rooting back to the question we had earlier, if the model is bigger, say again, the last part of the question?
Would that not just imply that knowledge on other agent actions is less important?
Yeah, no, not sure I understand. So my answer to this question earlier was that if you just have a big model, there's not necessarily a process where it's incentivized to encode information about the other agents. But when we learn the encoding, the embedding vectors, it's explicitly trained against a label that includes information from the other agents, like a reconstruction target. So you incentivize it to represent encode information about the other agent, and then you can condition on that, and so you can do interesting things. So, yeah, again, I think I'm not sure I follow the question there. There's also other interesting things you can do. When you have an explicit encoding, you can actually do unsupervised clustering in the encoding space, and you can then understand, for example, there's certain types of opponents. There's certain clusters of opponents, and they for example, everyone in this cluster tends to have a certain behavior, and our embeddings map into this cluster. So there's interesting things you can do with that as well. And you wouldn't be able to do this sort of clustering if you have just one gigantic policy, basically. But I guess I still don't quite fully understand the question made there. Maybe I can look at Slack later, and there's perhaps an online conversation I can follow up on. All right, I think let's do the break, and then let's come back in maybe 20 minutes at 11:50. Okay. Continuing on with the journey. Now we are in the final stages of the multi-agent RL journey, and we're going to be talking about a few more things, see how much we can do for the remaining 1 hour or so. And feel free to interrupt if you have questions, as always. Right. Now, we just talked about agent modeling, really important concept, really interesting idea. And now we're going to be doing something else, which is more about how to scale Marl and how to make it more efficient. And this is very important for practical reasons. Anyone here, if you want to use this in a scalable, actual way, parameter sharing and also experience sharing, which is something we developed in our lab, is kind of important to make it more efficient. Okay, so the problem is that training agents with Marl is difficult for environments with many agents due to the increased number of parameters to train. So, every agent has its networks for value functions and for policies and so on. So you have lots and lots of parameters, and lots of parameters are usually mean more and more difficult to train, basically, meaning that you need more data. So to approach this to improve the efficiency of the training many agents one is parameter sharing. This is when the agents actually share parts or the entire network parameters with each other. So that means that all of their data is used to train a shared model. So it's more efficient use of data and reduces the number of parameters. And then there's experience sharing as well, which is that agents, even if they do keep separate models, which might be a necessity in order to differentiate their behaviors, they still may be able to share experiences in order to train more efficiently. So we're going to be looking at this a little bit. First, parameter sharing. Okay, Parameter sharing and experience sharing assume that the agents are trying to learn similar or identical policies. That's typically the assumptions there, although we are doing research in some other labs too where they're trying to relax this. But let's just for now assume that we're looking at environments where the agents kind of either have to act similarly or they just are similar by definition. And we call these kinds of environments homogeneous. Okay, so that's just the typical term. There's actually two kinds of definitions that we introduce. Strongly homogeneous agents, this is what we define in the book, means that all agents have the same optimal policy. Okay, if we say that an optimal policy is with a star, then we say they all have the same optimal policy. And then we have weakly homogeneous agents. This is when agents can be permuted and their expected returns remain the same under the permutation. So it means that if you can sort of swap out their roles or their policies, then on expectation they still get the same return. That's what we call weakly homogeneous. So it means that the policies don't have to be equal, but it means that under the swapping out the roles of the agents or giving swapping out the different policies as a collection, they still get the same expected return. So let's look at some visuals here. Weakly homogeneous agents. Let's say there's a task where there's two agents, a red agent and a blue agent, and their task is to move their respective target locations. In this case, weakly homogeneous means that they can have separate policies. The blue agent needs to go here, and the red agent needs to go there. They're separate policies. But if we swap out those policies, they would still operate. So they would still function basically. And in that sense, they get the same expected returns. On the other hand, with strongly homogeneous agents, this is when the agents actually have the exact same optimal policy. So it means that the red agent's policy and the blue agent's policy, they do the same thing, basically. Okay. So parameter sharing visually looks like this. You can share network parameters across the agents. That's a common practice to make training more efficient. If you have no parameter sharing, which is what we've been doing implicitly so far, for your value functions, you have n different value functions, or a big network that is designed to function with n different sets of parameters, and each takes its own input history. So you have these separate networks. There's no sharing. With parameter sharing, on the other end, we just have one network that takes one set of parameters, but it can take any agent's input history. And you can also do things like you can condition it in addition to this index I, but you don't have to. So it depends on the application that you care about. So parameter sharing means we collapse these n different networks into one network that is shared among the agents, and they all get to input their individual history. Similarly, for policies, previously we had these n different policy networks with different sets of parameters phi, and they all took their own individual histories. And now we're collapsing that into one shared policy network with just one set of parameters, and you feed in any of the agent histories. And again, you could also condition this on the agent ID if you wanted to, depending on the application. So that's what it means to not share versus share. And you can see this drastically reduces the number of parameters. It's just one set of parameters that we're optimizing here versus n sets of parameters. Okay, so parameter sharing has two primary benefits. Scalability, number of parameters remains constant, independent of the number of agents. So that's a nice thing. It's not a function of n anymore. It's just one set of parameters. And efficiency, the shared parameters are updated using the experiences of all the agents, because all agents use the same models. The same model. It means that they all train that same model. And it means that all of their attention, all of their data goes into that one model, basically. So more trained data for the shared parameters. But the downside is that the naive parameter sharing assumes strongly homogeneous agents. And there's research that's trying to relax this by conditioning more efficiently on the agent index. But classically, that would be one of the downsides where you assume that they have identical policies. So can anyone guess why that is actually a downside? The fact that with naive parameter sharing, that it basically implies that there's strongly homogeneous agents, that they all have the exact same behavior. Why is that a problem for a teamwork situation? Anyone want to guess there?
For example, you have to divide and conquer. So each agent side have to do different tasks even to collaborate.
Yes, exactly. So, the real interesting teamwork tasks is when the agents have to do different things, different roles, complement each other. You do this, so I can do that, and then you can do this. Interesting teamwork like this. But if they have the exact same network and there's no way to differentiate the behaviors, then they're going to end up doing the exact same thing, and then there will be problems. They will not be able to differentiate these behaviors. And like a classical example that we often see is, let's say there's a navigation task in a warehouse, and there's like lots of shelves. And let's say I'm on this end of the shelf and you're over there at the shelf and we're both moving in and now there's a collision. Okay. And really the protocol should have been, okay, I'm going to let you do your thing first because maybe you're closer. And then when you're finished, I get to move in. Like there's a differentiation like this, right? Something of that nature. But if it's the exact same policies, we're just going to clash and keep colliding basically because we don't understand that we need to differentiate our behaviors. And that's a classical problem that you might see in some environments. Okay, let's look at an example here. Here's level-based foraging. There's just 2 agents and 1 apple. In this case, everyone has level 1, so they can actually do this thing on their own. Could just ignore the other guy. And here's a few different algorithms with the expected returns. So this is with the blue line is with the fully shared parameters when there's just 1 model. Then there's the shared parameters for only the critic for an actor-critic algorithm. This is A2C actually here. Then there's when we only share the actor, and then there's when there's no sharing at all. This is the line at the bottom. So you can see no sharing at all works worse than all the others. And then once you start sharing and sharing more and sharing everything, then you get more and more efficient in the training. You learn more quickly. But at the end, in terms of the limit performance, they actually all end up at the same place. And that's because sharing parameters does not necessarily give them better abilities. It just allows them to learn more efficiently. For example, you learn to increase performance early here because at this point, everyone's agent's experiences is used to train that shared model. Whereas with this last line here, it takes longer to increase performance because there's much fewer data that the individual models actually receive to train. So by sharing all the data, you can make progress more quickly. Question there, yeah.
Just a clarification, when we share parameters, the gradients are computed on the experiences of all agents, right?
Yes.
So
Yeah.
we take a mean of the gradients of all the agents.
Yes.
Thank you.
I mean, there's different ways of doing this. If you have a method that's, for example, based on a buffer, then you would sample from that shared buffer, basically. But it comes to the same thing as what you're suggesting. Okay, so under experience sharing, agents will learn separate policies and value functions, but their trajectories allow for training on the collective data. So what do I mean? Parameter sharing means we have the same model. Okay, so by extension, all the data will be shared because it's used to train that same model. But there can be problems because if we have the exact same behavior, then we're not able to differentiate behaviors. So we need that ability. So now let's say, okay, we want to have separate models. We want them to learn their own behaviors, but we still want to gain from the benefit of sharing data so that we can train more efficiently. Kind of seems like we should still be possible, right? And that's the idea of experience sharing. Experience sharing means that we may not have the same models. We have our own parameters, but we still want to be able to share and make use of each other's experiences. So an assumption is that the agents are at least weakly homogeneous, which means that they learn similar policies or have their experiences are related to one another. It doesn't make sense to share experiences if you're doing something completely different from what I have to do. Then there's nothing I can learn from you, right? So there's an implicit assumption that in some sense what you're doing needs to relate or like be similar to what I'm doing, so I can learn from your experiences. There's an important note here, which is that the experiences of agent J are off policy, because agent J has a different policy from me, which means there's a different distribution of actions for that agent, and I need to be correcting for that when I use this agent's data. So how do we do this? There's two ways to do this. I can either use off-policy RL algorithms like Q-learning, and then I don't have to do any correction because that's the nature of off-policy. I can use data that's not coming from my policy. Or if it's an on-policy algorithm, then I need to do a distribution shift correction. And a classical way of doing this is using a technique called importance sampling, which is a very simple technique. Okay, so let's first look at an off-policy algorithm, which is DQN, which uses the replay buffer and makes it off-policy. Independent DQN means that everyone uses a copy of DQN. You know this already. And we have this experience sharing by doing these steps. First, we collect all the experiences of all the agents in a shared replay buffer. We call this D-shared. It's just a replay buffer, just like before, but it now has the experiences of all the different N agents. Then every agent samples from that shared replay buffer to update its value function. So when it samples the mini batch, it can contain data from all the different agents. And then each agent optimizes its value function using the typical DQN loss, so where you have the temporal difference target, as before. So DQN is an off-policy algorithm. It uses the replay buffer. So theoretically, it's able to handle this idea that the other agents use other policies, and it's off policy. It's more interesting if you use shared experience with actor-critic algorithms, where you have an on-policy component. And this work, actually, we developed this first in Nirup's paper in 2021, I think. And a lot of people have subsequently followed up on that. But basically, we showed how to do this with an on-policy algorithm by using a statistical technique called importance sampling. So we can also extend independent actor-critic algorithms like independent advantage actor-critic or independent PPO with experience sharing by optimizing the loss over the data of all agents. But now there's this problem that the data from these other agents comes from their policies. And that means I cannot just naively use their data because their policies are different from mine. So there's a different distribution of their experiences. I need to change something. So SEAC, which is this algorithm shared experience actor-critic, we call it that, spelled out up here. It uses a policy loss, which is similar to the policy gradient for an independent actor-critic, but with importance sampling to do this distribution correction. So it looks like this. This is the loss function for the policy parameters phi I, and it's spelled out here. This is basically from the policy gradient. We have our immediate reward plus the bootstrapped value estimate from the successor, and this whole expression here makes the temporal difference. This is the TD update, and the whole thing is called the TD error. And then this is from the policy gradient theorem that we discovered or that we described earlier. So this is the first part of the new loss, and that cell uses agent I's own data. So we're optimizing the parameter for agent I, and it's using only the history or the data of that agent I. And the change that we now make, it looks like this. It's now a bigger loss that applies the same policy gradient definition that we see here, basically down here in this other box. But there's a slight but important change. Now we're doing this application of the policy gradient with respect to the data of this other agent K that we're using, but still optimizing our own parameters for this agent I. Okay, so we're using our parameters to do a value estimate for the bootstrap target here. But actually, we're doing this over the data of this other agent. And so now the problem is that this data from this other agent comes from their distribution. There's a distribution shift. And we're correcting for this shift by using this importance sampling step, which is just this ratio between the policy from the agent that we're optimizing for and the policy from the other agent whose data it is, agent K. And we have access to this policy during centralized training. Okay. After training, we don't have access to this anymore, but it's not important. We don't need it anymore. So that's all. That's the whole new construction. This is what we had before experience sharing, only using your own data. We're applying the exact same thing to the data of the other agent as well, still using our parameters, but using the other agent's data. This data now needs to be shifted by using an importance sampling step, which is just this ratio here. And then we just add it all. It's just a sum, and we add it to this. There's also a coefficient lambda, which we can use to weight the importance of the data from the other guys. So naively, you could say 1, or you can use a smaller value to say, okay, my data is more important than the other guy's data. You can also have interesting protocols. So for example, one of my postdocs, he's developing a new protocol where he wants to automatically learn the lambda values for the different other agents. And then you can have more flexible protocols where we can say, okay, I want to share with you because you're doing something that relates to me, but I don't want to share with you because maybe you're doing something else. So you want to have a smart agent that can figure this out. In this case, it's just the basic idea. So we're going to set this to 1, and it just means that your experience is the same importance as your experience, basically. It's like a naive way of sharing. Okay. Yeah, so that's the end of the parameter sharing and the experience sharing idea. I think we've got a minute for questions about that. Any questions about parameter sharing, experience sharing? There.
That was the actor loss. What about the critic loss?
Yes, that will be a very similar thing for the critic loss as well, which I skipped over here because it would have been a lot of stuff. But good observation, good question. Yeah.
Thank you.
You can find all this in the book and in the paper as well. Other question? Nope, nope. Hand there, yeah.
Why did well in the graph it seemed like actor like parameter sharing for actors had a quite bigger impact than for critics.
Oh yeah. Here you mean?
Yeah.
Yeah.
Is there any pattern there or it's not? No, is there not?
Yeah, interesting question. I don't know. I think I would have to think more about this. I mean, it's known that in some cases the critic is more important than the actor in terms of how accurate it needs to be. It's also known that in some cases learning a critic can be easier or harder than learning an actor. It kind of depends on the properties of the environment. So if you go back to the original reinforcement learning book by Rich Sutton and Andy Bartow, they already explained this idea that sometimes you may want to prefer a value-based algorithm because it's easier to learn values. And sometimes you prefer to use a policy gradient algorithm because it's easier to learn policies without the values. And I think it's still kind of an open question, to be honest, in reinforcement learning to understand when that is the case. It's kind of still one of the engineering aspects. You need to try and see what works. So in short, I don't really know. I don't have a strong answer, but it would be an interesting question to analyze this. If there is like masters or PhD students here who care about this, maybe there's a cool like project that you can do. Okay, so let's move on. Okay, so now we're going to go into policy self-play in zero-sum games, and it gets really interesting now. This is something a little bit more very close to some of the real state-of-the-art that we have seen in recent years. So let's now look at zero-sum board games, like chess and like Go. I think everyone here knows chess. Maybe not everyone here knows Go. Go is a Chinese kind of chess, which is much more complex than chess in terms of the branching factor. So this, nominally speaking, is much more complicated for our brains than this, basically. Although a difference is that here you only have one type of piece and here you have lots of different types of pieces. Anyway, these are turn-based zero-sum board games. We're going to look at them now. These games are difficult for a few different reasons, and you can relate to this. One is these games have sparse rewards. So agents only get a reward once the game terminates. You get a +1 if you win, you get -1 if you lose, you get 0 if you draw. And until that point, you get nothing. Okay, it's kind of difficult, right? If you think about it. Then there's a large action space, very large action space. So many of these board games, basically agents can choose from a large action space, which is moving all the particular pieces into the different places. If you look at this again here, you could move any one of these pieces to a certain range of locations. So it's a large action space, big branching factors. And then lastly, there's a long horizon, which means that these episodes can last for many, many time steps before you actually reach the end of the game, like losing or winning. Could be tens or even hundreds of time steps, right, in terms of making moves. So the combination of sparse rewards, large branching factor, and long horizons leads to some really difficult to explore, huge search trees. Okay, very difficult to solve these things for humans in any meaningful or analytical way. The only way for us to deal with these kinds of complexities is if we have very specified heuristics and we get trained and, with all kinds of rules of thumb, basically. Okay, so fortunately, we can exploit the structure of these games to develop some efficient algorithms, and that's been done in AI research for some time now. The most common way to address these kinds of turn-based board games is by using tree-based search, tree search. Okay, some of you may be familiar with this already, but it kind of looks like this. There will be an initial state as 0. That's where we start. And then there's a branching, which is all the different actions you can try, action 1, action 2, and so on. Depending on the action you try, you get to a successor state in your tree, and then you can try the next actions and so on. So that's where this tree comes from. There will be nodes corresponding to the board game states, and there will be the branchings, which are the different actions you can try. And then you can expand the tree like this, right? You can also have the turn-based nature, which means that in some of the nodes the agent 1 gets to pick, and the other nodes agent 2 gets to pick. This is typically what happens in these turn-based games. So we can use turn-based zero-sum games as trees, where there's the nodes corresponding to the states, edges represent the actions, and leaves represent the terminal states. At some point at the end, you will reach a terminal state, which is when you win, lose, or there's a draw. And the different agents get to pick actions in the different nodes. So this is difficult because the trees can grow very large. This is what I just explained. It can be very deep if there's a long sequence of steps required, and also can be very broad if there's a big branching factor. So it's not just the case that we have 2 actions. We have many tens of possible actions, huge branching factor. Monte Carlo tree search is a way to make this a bit more tractable by using sampling-based approximations. Can I ask hands up if you know MCTS? Who knows MCTS? Okay, some people know it. Just a little bit under half. So this is kind of an important canonical technique in AI that I think pretty much most people should actually know about, at least a little bit, because it's very, very broadly applicable. And in fact, I'm actually kind of a proponent for just saying that MCTS is just reinforcement learning. Okay, let me explain in a minute what I mean by that. But still, it was developed in a different community and they have their own language. Okay, so MCTS, Monte Carlo tree search. You can already kind of guess what it's doing. Tree search is what we just saw. Monte Carlo, we learned yesterday, it means sampling based. I think someone explained it's about casinos or something, but it's sampling based, randomized. MCTS consists of 3 key steps. First, simulation. You simulate the game from the current state to a leaf node. Okay, you simulate like how you might get down this tree. Then, expansion. Oh, I think I need to make a note. I forgot the colon here. Just a sec. Okay. Expansion. So then you will actually get to grow the tree. So the tree might be very small in the initial search spaces. So when you hit a node that hasn't, or when you hit a state that hasn't been represented in the tree yet, then you can add a new node to represent that state in the tree, basically. So you grow dynamically the tree. And then there's backpropagation. Once you hit a certain state, for example, after you've added a node or once you reach the terminal node, then you need to backpropagate the values, the rewards from the leaf node, the bottom node, all the way back up to the root node where you started. Okay, so MCTS maintains 2 statistics in order to do this. For each visited state action pair, you have your value estimates. This looks very similar already to reinforcement learning, which is what you know, which is the expected returns for action A in that state S. And then you also have your visitation counts. How many times have I tried that action in that particular state? MCTS generates then K simulations from the current state. Simulations just means you sample down the tree, different trajectories. And by sampling actions according to a policy, it's called like a exploration policy, basically, until a leaf node is reached, a leaf node in that current tree. And the leaf nodes that are basically are previously unvisited terminal states. So to sample these actions in the tree, you have this tree, you're trying to expand and sample down in that tree to explore the different directions. There's 3 different policies. Of course, you could do epsilon greedy, which is, again, already you know this from reinforcement learning. Or there's another technique called upper confidence bounds, which is slightly more complicated, but it's another way to explore actions. And you can use that in reinforcement learning as well, but it turns out it's quite commonly used in MCTS. And more graphically, it looks like this. Okay, so we're in this tree. Let's say we start from here. This is where we currently start. We explore an action with our exploration policy, like epsilon greedy, explore action, until we hit a new state that we haven't represented in the tree yet. Basically, then we add a new node. We initialize this new node to add to the tree. And to initialize that, we add a new counter, which is 0 initially, of course. And then also a new Q function here, which can be initialized to be, for example, 0 or some other heuristics. Then once you added that node, you backprop the value from that node up all the way up through the nodes that you've previously visited. That's the backpropagation step. And in fact, this actually works exactly the same way as reinforcement learning. You can use the same statistical backpropagation operators like temporal difference learning that we've experienced, that we saw earlier in Q-learning, for example. So for each visited state, this is this trajectory here, for each visited state action pair, we increase the visitation count and update the value at estimated that node by doing this incremental update. Okay, this is the exact same as what we do in Q-learning, except that here it's not a constant alpha, it's actually the ratio. This is actually a good thing because it means it satisfies the approximation conditions that I introduced earlier. And this is the sample return at that time. So it could be a TD update, or it could be the sample return exactly. So any reinforcement learning temporal difference update rule can actually be used here. Okay. Simulation expansion and backpropagation, these steps that I just showed, they're repeated every time step. So you are in the game. There's a time step T where you get to make a move. And every time after you've made a move, you basically do this, or before you make the move, you do this simulation expansion and backpropagation. You will have a certain budget. For example, let's say you can do 10 simulations, 100 simulations, or you have worth 2 minutes, 10 minutes to make your choice. And whatever your budget is, that's how many simulations you can actually run. And basically, the more time you get, the more you can run, and then you get better quality outcomes to iteratively grow the tree. So following case simulations, let's say that's the budget you have. You're allowed to do case simulations at every time step. From the current step T, state T, the best action is then selected. And that's kind of straightforward. Either this could be just the argmax greedy action at that point in time, which is what we've done before, or it could actually be the action that was visited most often. And some people prefer to do that for some reasons. I'm not sure quite why, but the reinforcement learning approach would be to do this here. Okay, so in terms of the pseudocode, it looks like this. This is Monte Carlo tree search for MDPs, which is single agent. And the same algorithm can be used for two-player zero-sum games when there's the idea that one player gets to make a move at every point in time. So it's actually then reducible to a single agent setting, and it's explained a little bit more in the book as well. But let's look at how this works. First, we repeat for every episode. You go through a number of time steps, T0, 1, 2, 3, and so on. At every time step, you get to observe your state, and then you do in that state your K simulations. K is just a parameter. That's what the budget is that you have. You're allowed to do K simulations. You know, the higher the better. Okay, and then basically you do your simulations. You perform your simulation. You do your explore action. You go down the tree. You simulate what the successor states will be, and so on. And until you hit a node that doesn't exist in the tree, then you initialize that node. That's what I just showed you earlier. You expand the tree, you add a node, you initialize that. And then you do your back propagation, which is when you go reverse direction, you go back through time basically in your trajectory, and you update the nodes along the way by updating the state visitation counts and the Q functions. And you do this for a number of simulations, and at the end, you get to pick your best action for the current state that you're in. For example, the one that has the highest Q value. Okay, MCTS assumes that you know the transition function T because you do your simulations. It assumes that you know the reward function as well. And it can learn estimates. You could actually learn estimates of these things if you wanted to, but you know, in these games like chess, you actually know the transition function. It's nothing to learn. You know this already. Okay, so now it gets a bit more interesting. This was just the backdrop before we do any of the multi-agent stuff. So far, I've only shown you MCTS for a single agent MDP and kind of how it works. Like it does these rollouts, it explores the environment, it does these statistics. It's basically just a reinforcement learning approach. And now we want to make this for two-player zero-sum games like chess or Go. And how do we do this? First thing to say is that that we're looking at zero-sum games with symmetrical roles and egocentric observations. What do we mean by that? Chess is an example of this, or nearly actually an example of this. So the idea is that we have these two players. They have the same kinds of pieces, and basically, one player can just put itself into the perspective of the other player, meaning that one player can use its policy if it put itself into the perspective of this other player. So this is from agent 1's perspective. And then from agent 2's perspective, we can basically just rotate the board and change the colors. And then we have agent 2's perspective. You can see, you know, these are the same pieces that we have up here. We just rotate the board and change the colors. The reason why this is important, if we're able to make this transformation due to the symmetry, then it means we can use the same policy from agent 1 to also sample an action for agent 2 as if it was putting itself into the perspective of agent 2. The policy is then still well defined because of still the same perspective, the same representation. That's why this is important. If this property didn't exist in the game, then we wouldn't be able to use agent 1's policy for agent 2 without this kind of transformation. So the reason why we care about this is because we want to now have a training regime that's called policy self-play, which means agent 1 is actually training against a copy of its own policy. And by doing that, it's learning its own weaknesses and to close its own weaknesses, basically. Okay? Do you feel this makes sense, what I just try to explain? I wonder there's probably other ways to explain this, but this is kind of how I like to think about this idea that the game is symmetrical and can be rotated so that I can just shift perspective. Now I'm looking at your perspective. I can rotate the game board, basically. Makes sense, right? Okay, question?
So in this case, if you're kind of playing against your own policy, would you kind of run into like an overfitting kind of scenario where, you're only good against yourself and not against, like a general opponent?
Yes, very good question. For that reason, you actually do more than just train against your own policy. You train against also copies of your past versions and maybe distributions of policies. So you want to remain a bit more robust. Good question. Yeah, exactly.
All right. Yeah, thank you.
Yeah, and that actually goes into, after this, we're going to be talking about population-based training, which goes exactly to what you just described. Okay, so the idea here was just to set the scene. We want to be able to train in a way that where we basically train against a copy of our own agent. And that requires that we have an environment where we can put ourselves into the perspective of this other agent by rotating the board, basically. And that allows us to use our exact same policy as if we were in that agent's perspective. Okay, and that's basically this whole thing, this MCTS that I just explained, plus the idea that we're going to use our policy for ourselves and for the other agent using this MCTS approach is exactly what AlphaZero does. AlphaZero is an algorithm that came out in 2018, was developed by DeepMind. It was actually a follow-up algorithm to some previous algorithms which were published in 2015 in Nature, where they successfully defeated the world champion in Go, which was not done until that point. But AlphaZero is more interesting than this previous work because it generalizes much more to all kinds of two-agent zero-sum board games, and it's much simpler than the original algorithm that they published in the Nature paper. So that's why we focus on AlphaZero. So what does it do? AlphaZero combines self-play MCTS. It uses this MCTS algorithm that I showed you, but it uses the same copy for agent 1, also for agent 2, by putting itself into the perspective of agent 2. You can use the exact same MCTS algorithm. And it also uses deep learning to learn value estimates for, when you add a new node, you need to add the value estimate at that point, and you can actually use deep reinforcement learning methods to do that. And by doing this combination, they were able to train a model that reached superhuman performance in Go. In fact, they had a budget. I'm not sure exactly what that was. I think at every point in time, they were allowed to do a few hundred rollouts, I think, if I remember correctly, something like 300 or so. And that was enough budget, basically, for the agent to learn accurate enough and strong enough models. In the book, we describe more of the settings, in terms of how deeply they were able to roll out, what the budget was, what the winning rates were, and so on. You can find that all in the book. But the fact is, with this very basic combination of techniques, they were able to produce an algorithm that is very strong for these kinds of games, is scalable, and is actually applicable to a range of games, not just Go. You can apply it to all kinds of games that have this property of symmetry and zero sum. So it's a very interesting algorithm for that reason that is really worth studying. So what does it do in addition to this self-play MCTS? There's this value function learning. Basically, there's a deep network with parameters theta, condition on state S, and it's doing two things at the same time. It's giving a value estimate for that particular state and also produces the action distribution of that particular state, which is the policy. For each episode, there's this data that's collected. It's probably not so important for the rest of this lecture, but for completeness, we're going to do this anyway. So you collect your states from your MCTS. You have your policy distributions also computed by your best action function at each of the states. And then you have your Z is the outcome at that point. So it's like a reward, +1 for win, -1 for loss, and 0 for draw. This is what you get at your terminal node, what you want to back propagate, basically. And you're learning a single network that is actually representing all this information in the value network and in the policy. The single network is randomly initialized and then has a few losses which are combined linearly. So here's the combined loss. There's the value loss, which we use to compute the Q function. There's a policy loss, which we use to compute the policy distribution. And then there's a regularizer here at the end, which is basically used to control the complexity of the function we're using it. So it's not very important to understand what this does here. The value loss is as before. It's just basically a TD a temporal differencing target. And then there's the policy loss, which is when we actually want to maximize the probability of choosing certain actions. I think for the purposes of this lecture, it's not very important to go through all these details because they could be changed and modified. The main point to take away really is that we have an MCTS process that is using a self-play approach, which means that our policy is used for myself and also for this other agent to pretend like we are in this other agent's shoes. I think I want to leave it at that in terms of the self-play. Let's look at this population-based training now, which is really quite interesting. I think it's more interesting than the self-play because this generalizes the self-play idea. So let's look at this instead for the remaining time we have. Population-based training. I think this is a really important approach in multi-agent reinforcement learning, and it can be done in many different ways. So what's the motivation? In MCTS, we focused on policy self-play in 2-agent zero-sum games, like chess and Go and shogi, for example. And we want to extend this idea to self-play in general sum games with more than 2 agents. So it could be more than 2 agents, but it also doesn't have to be zero-sum. Population-based training extends this idea that we just saw to exactly allow this kind of setting. It's a generalization of self-play to general sum games. And the way it works is as follows. So you maintain these populations of policies. It gets back to the question that we had earlier. Population of policies representing possible policies that the other agents can have. So every agent has a set of policies that they could be having. And we evolve these populations over time through a number of different generations, as they would call it. This term generation comes from this survival of the fittest kind of idea. We denote the population of the policies for agent I by using this uppercase pi notation here. So this is the population for agent I at generation K. And the broader overview of population-based training looks like this. Before we talk about a specific algorithm, let's just look at the general steps. First, we initialize the populations of the policies for each agent. For example, initially every population could just have a random policy in there. And then we go through our iterations. The iterations, which is the number K, follows 2 steps. Each generation has these 2 steps. First, we need to evaluate the fitness of these policies in each population. So we evaluate the performance of the policies in a population by playing against the policies of the other agents in their populations. Okay, it's like a cross-population evaluation. We want to understand the fitness, the goodness of the current policies in the populations. And then we do our evolution from generation K to generation K+1, which means we change the populations. And that's basically can be done in a number of different ways. But the idea is that we want to remove certain policies and maybe modify and add certain other policies that we think are high performing. Typical ways of doing this is things like mutating existing policies or adding other new policies in other kinds of ways. So this process is repeated until we converge or for a fixed number of generations. All of the population-based training approaches, in some sense, instantiate this process where you go through your generations and you have your evaluation and evolution task. And then again, evaluation and evolution tasks. That's kind of how you evolve the policies over time. We're going to be looking at one specific algorithm, which I really like, and we've decided to represent this in the book because it's a nice, simple to understand, but very general representation of this population-based training approach. It's called PSRO, which stands for Policy Space Response Oracles. It's kind of a complicated name, but it's the method is actually not so complicated. So how does it work? Let's go through this step by step. First, as before, we need to initialize the populations. And let's just say we initialize them randomly. Every population for every agent has just a random policy in there. You can do this easily. And then now it gets interesting. In the second step, this is when we now prepare the evaluation and the evolution steps. We construct this meta game uppercase M at generation K, which looks like this here. This basically is a normal form game where we have one dimension for each agent. So in this case, it's an example for 2 agents, 1 and 2. So there's only these 2 dimensions. And what they have in this normal form game is this action space corresponding to the current policies in their populations. Okay, so if this is agent 1 here, and at that generation, it has this many policies in its population. We're saying in this meta game that each action corresponds to choosing that particular policy. Okay, first action is to choose that particular policy in the population. The second action is to choose that particular policy in the population, and so on. And the same thing we do for agent 2. It will have a certain number of policies in its population, and we're going to represent that by having each policy represented as an action. You can see this is just a matrix game. Okay, we need to also now have these rewards in here in the matrix game. And that can actually be computed by playing these policies against one another. So I'm playing these 2 policies against each other, and then I get these expected returns for the 2 different agents. I do this for all possible combinations of policies. Does that make sense for people? This is the so-called meta game. And basically it just represents the 2 different populations as actions, and then these are the expected returns for the different agents if these respective policies are playing against each other. Make sense? Everyone make sense? Okay. So you can kind of see probably where we're going with this already. There's a reason why we want to have a matrix or a normal form game representation. We can then do some interesting operations on that, like computing equilibrium solutions. And that's what we're doing now in the next step. Oh, there's one more thing as well. So in order to produce this matrix normal form game, of course, we need to get these numbers from somewhere. And like a simple way to do this is basically by running multiple episodes where they play against each other, and then we average those numbers. In this particular example I'm showing you here, I just made up some numbers that look very clean. In practice, these numbers would be more complicated kinds of scalars, not so clean numbers, not integers like this. But anyway, the idea is that we play them against each other, like this against this, and then we repeat this a number of times, and we take the average expected returns, and that's going to be that entry in the matrix. We do this for all possible combinations. Okay, now we do something interesting with this metagame. Once we have this defined, which is all the agents with all their actions corresponding to their policies and all the rewards inside here, we can now do things like computing a Nash equilibrium or computing a minimax profile or computing other kinds of solutions in this particular game. So we have this normal form game, we compute a solution concept like a Nash equilibrium, and that in turn gives us the distributions. Let's just use delta in this case, and we kind of represented this with these bars. These bars are supposed to represent different probabilities that the Nash equilibrium or the solution would give to these particular actions here. Okay. So kind of, if you think about it, this delta is like a meta joint policy. It's a distribution over the different policies that you can actually pick in the populations of the agents. Okay, so these probabilities here together define a Nash equilibrium, if that's the solution concept that we've picked. And now we can use this to do the expansion step in the populations, or the evolution step, as it was called. So basically, for each agent, we want to add a new policy now in their population. The simplest thing is that you just add one new policy. You could add others as well. And how do we do this? Well, basically, every agent I determines an effective oracle policy, as it's called. That's where this name comes from, PSRO, which is a pi prime, against the solution distribution of the other agents, basically when you fix that. So basically, from agent 1's perspective, let's say we fix a distribution over the other agent's policies. This is what we just got here. This is that distribution. And then we train an optimal policy against that distribution of policies of the other agents. So it's basically a single agent problem at that point. We fix the other agent's policies using that distribution. We can sample their policies using that distribution. And then we only need to learn one single agent policy for our guy, whilst keeping the other agent's policies fixed according to their distribution that we computed in the Nash equilibrium here. And then we compute an optimal policy, which is the best response policy that we then add here. This is the new one here. Similarly, for the other agents, we do the same process. Then we end up with these question marks. We need to add some new numbers here, and we do that simply by doing the same thing that we did before. We play our new policy against all these other policies, and we average the returns, and then we add the numbers here just as we did before. So we've now expanded the populations. Each population now has one additional best response policy, and we also expanded the size of this meta game. And that's it, basically. That's the whole idea of the PSRO. Okay, I just explained that. So here's the pseudocode. Let's go through this step by step. Okay, so we initialize the populations. Every agent has an initial population. The initial generation is just 1, and this is for every agent I, and this could be just a random policy. Then we go through our generations, K1, 2, 3, and so on. We construct the metagame at that particular generation. This is the image that I just showed you, using the existing populations. Then we use a metagame solver, like in Nash equilibrium, to give us these blue-barred distributions. And then for every agent, we compute a best response policy against the other agents' policies using the distribution over their policies from the Nash equilibrium. We can get a best response policy that we add to our own population if it's not already in there. And that's it. We do this for a number of iterations until we converge. Convergence usually would happen if none of the new best response policies that we computed weren't already included in the respective populations. Okay, does this pseudocode make sense for people? Question there? Remove policy.
Yeah, remove like in the genetic algorithm, like the less fit policy will be removed from the matrix game. We will have less.
I think removal happens implicitly if, for example, a Nash equilibrium assigns 0 probability to a particular policy, because it kind of means like you would never pick it. It's probably not good. And I guess at that point, you could decide to actually take it out from the distribution. Yeah.
Because you will still need to compute the match when you add a new policy.
Yeah, because if it's a 0 probability anyway, then it doesn't affect the best response policy. So I guess you're right. At that point, you could probably take it out. But the reason why it's not done is because theoretically speaking, we need to keep track of what past policies we've produced so that we have a termination condition. The termination condition is that if there's a new policy that's already included in the population, then we stop at that point, basically, if that's the case for all the agents. So that is the reason that I'm thinking why you probably don't want to remove, theoretically speaking. But practically speaking, you probably could do this. Yes.
Thank you.
Okay, so moving on. So PSRO computes the, we want to see now what's happening theoretically speaking. And let's say we're looking at the rock, paper, scissors example. In theory, if PSRO computes exact Nash equilibrium, so this might not be possible because there might be irrational numbers, but let's say exact Nash equilibrium. And if it computes exact best response policies, with reinforcement learning, we could do this. Then the population distributions of PSRO converge to a Nash equilibrium of the underlying game. That's an interesting result, an interesting theoretical result. Okay, there's some ifs here, but if those ifs hold, then we know that this converges to the actual Nash equilibrium of the underlying game, which could be like a big partially observable stochastic game. So let's look at this in an example of rock, paper, scissors. Let me walk you through this step by step. First of all, in this table here, there's K. K is the number of generations. So 1, 2, 3, 4, 5. These are the generations we're going through. Then there's this pi1 and pi2. These are the two policies of the two agents, okay? Agent 1's population and agent 2 population. And you can see that we're going to be using deterministic policies. So that's why we just write the letters of the actions, rock, papers, and scissors. So initially, there's just a rock action in here, which is the deterministic policy that chooses rock. And for agent 2, there's just the paper action here, which is the deterministic policy that uses paper. It's just randomly initialized. So if we're looking at this first iteration, only looking at this first row here, then you can see the Nash equilibrium, of course, trivially becomes a distribution of 1, 1, because there's only these two actions that policies that can be picked. So now we need to add the new policies, which are the best response policies. For agent 1, the best response policy against agent 2 is scissors, because scissors beats paper. And for agent 2, the best response policy against the population of agent 1 is paper, because paper beats rock. So now we're adding these two new best response policies. For agent 1, the new policy is scissors, is added now into the population. And for agent 2, we already had paper in there, so there's nothing to add here. Now we compute the new Nash equilibrium, which looks like this. The new Nash equilibrium would pick deterministically, put all mass on the scissors action, and trivially put mass 1 on the paper's action because there's a 1 action. So now the new best responses look like this. The best response for paper is still scissors. And the new best response for agent 2 against this distribution over these two policies here is now to choose rock, because the probability is 1 for scissors and rock beats scissors. So now we go on. We add scissors was already included in the population here, but rock was not included in the population here, so we add that. And you can see how it goes on like this. We repeat the process, and at some point we're going to be in a place where all 3 actions are actually included in both of these populations. And then the unique Nash equilibrium that we compute is the uniform distribution. So at that point, the best response will again be to play uniformly, and that means the distribution, the policies are already in there. And we finished. This is a determination criterion. So you can see that at that point, the uniform distribution over these deterministic actions is exactly the Nash equilibrium in both cases. And it's a nice sort of step-by-step example of how, in this case, we actually converge neatly to a Nash equilibrium. It's maybe not a particularly efficient way to compute a Nash equilibrium, but it does guarantee you that you get a Nash equilibrium. And the reason why this is actually interesting in the bigger picture is because this is just a matrix game example. But we have the same guarantee of converging to a Nash equilibrium in theory, even if the underlying game where we sample the policies is a big, complicated, partially observable stochastic game. So that's why that's interesting. So here's an example of a big, complicated, partially observable stochastic game. It's StarCraft II. StarCraft II, I think I showed you a video at the beginning, and I explained there's the StarCraft II algorithm that was developed called AlphaStar, and it actually was a very strong player against some really advanced human players, like professional players. And it's designed to play the whole game of StarCraft, which means you do the whole thing. You do your base construction, your resource collection, your unit construction, exploring the world to understand the map and so on, and then trying to harass your opponent and sort of defeat your opponent. So the whole thing, like you play the whole game. And it's using an approach based on PSRO. Okay, StarCraft II is challenging, similarly to what we saw before, because of the sparse rewards, because of the large action spaces, very large action spaces, in fact, and because of the really, really long horizons, much, much longer than what you would see in chess or Go, because these games can last for thousands of time steps. There's also partial observability. This is new now. We didn't have this before. Now we have partial observability because there's this fog of war. Okay, it means that there are certain things in the world that I don't actually see. And there's also a huge diversity of strategies that you can actually employ here. So it's a difficult, hard game to beat. AlphaStar does a few things. First of all, it pre-trains some policies for each race using supervised imitation learning. It means we assume that we have access to some human trajectories. It's just a way basically to make the learning a bit easier by having a good starting point. These imitation learn policies aren't particularly strong, but they are much better than starting random, basically. And then after the pre-training, AlphaStar does basically a population-based training, just like PSRO, but they call it differently. They call it league training. They have these 3 categories of agents populations that they train. So they have these main agents, which are largely trained in self-play against any prior policy. Then they have the exploiter agents, which are designed to exploit, the main agents. Then they have the league exploiter agents. It's not very important, actually, for us, to be honest. And, this is just what they made up. They made up these different categories of populations. But generally speaking, it's a population-based training algorithm, and you could have come up with other kinds of protocols which are just like that. The idea being that every agent has a policy that is trained against other kinds of populations of policies to have a broad diversity of opponents that you need to be optimized against. So this is not very important, actually, exactly these kinds of names they have and how they define this. There's also something else they do. They need to, of course, sample basically from the different distribution. They call this prioritized fictitious play. Again, I think it's not particularly important for this. It's just a different way of sampling the opponents from their policies. I think what I want to just say at the end of this is AlphaStar is a really interesting example of a population-based multi-agent reinforcement learning algorithm that was able for the first time to scale and beat a really big, complex, complicated game where there's entire human professionals that make a living of playing a game like this. Okay? And it's much, much more complicated than chess and Go, because now you have much bigger horizons, much bigger branching factor, partial observability, stochastic effects, and so on. It's really complicated. But it's very impressive they were able to pull this off with something like a population-based training approach. And I think population-based training can be applied to a whole range of applications if you can come up with a smart way to design these populations. Of course, it's also a very expensive way to do this. You need some expensive infrastructure to do this kind of computation. So this brings me now just in time to the end of the whole lecture. Really pleased that we were able to manage to do this in time. I want to see, first of all, if there's more questions about the material that we've just covered. So population-based training, policy-based self-play, or these other topics that we've had. Any questions? Or online? A question there?
I do have a question about parameter sharing.
Okay.
What will it look like with this kind of population-based training? Will the population could share also the parameters, or?
Yeah, I guess not. It depends. Because if you have fully shared models, it means that there's only this one behavior. But the point of the populations is that you want to represent different kinds of behaviors. So a naive, fully shared parameter approach probably would not make sense. You need to, if you do end up using parameter sharing, you still need to have some ability to differentiate behaviors. For example, by having some sort of agent ID as an input. And hopefully you can still learn to develop different behaviors. But for that reason, I guess you would not do that because it means that it would just be one behavior in that population.
Also the category maybe that they did like with the different type of agents, will they share among a subset of policies?
I don't remember if they did this. Maybe they did something like that. Yeah, I don't recall. I mean, there's lots of implementation details. If you look at these papers for AlphaStar and AlphaZero, the papers are not reproducible. I can tell you from experience because I've tried. We've contacted the developers. They were not very forthcoming with some of the details. We spoke with the guys at DeepMind. They were very sort of salami tactic. They didn't provide a lot of details. It's kind of frustrating, to be honest, if you think about it. Like it should be reproducible with the publication, but it's for sure not. I can tell you this, and including with the supplementary material in the paper. So the fact is, these things require actually still a whole lot of engineering tricks and special sauce. And even the stuff that they have in the paper doesn't even include all the special sauce that they did, basically, at least not to an extent that it's reproducible. So the only way we could actually write about this confidently in the book is by, first, we had to interrogate the developers as much as we could. And then I still didn't feel happy. So I instructed a bunch of undergraduate students to go and build the whole thing. And then they came back to me, and if they all told me the same thing, then I felt confident that, yes, that's the missing pieces that they didn't tell me was in the paper, basically. Yeah, kind of frustrating, right? It's actually a big problem with deep reinforcement learning as a community, I think. The whole community suffers from problems with reproducibility, which is in general a problem with machine learning, I think. So that's why in my research group, for example, and I encourage all of you to do this as well, we have a really strict policy in terms of transparency and reproducibility. So what does that mean? There's also a blog post. Completely all of the code needs to be open sourced and available, but not just dumped. It needs to be clean and documented, and there needs to be a README file that explains exactly how to reproduce every single experiment so that you can actually do it step by step. We also release all the data from all the experiments in our data repository, so you can go ahead and inspect and do your own hypothesis testing and everything and so on. And we also have other sort of extra rules for transparency in terms of providing support and so on. I encourage all of you to do this, right? So everyone, when you publish a paper, or even if you dump on an archive, have a nicely documented code repository with the complete code, including the description of the algorithms and how to run it step by step to get exactly the experiments that you have in your papers, basically, just as a meta comment. So I think if you all follow that rule, it would already go a long way to reduce these reproducibility problems. Yeah, sorry, it was a side comment there. I got off track there. Question there. Or there? Yeah, sure.
Just a general question. You mentioned, these things are computationally expensive. So what kind of expectation should I have, like, if I wanna, like, run these algorithms and stuff? Like, can I run it on a local machine? Do I need a cluster? Do I need to get a supercomputer? Can you maybe comment more on that?
Yeah, for sure you cannot run this on your laptop. Yeah, I mean, you could maybe if you come back in a couple of years or so, something like that. But no, you need like high-powered server systems, and it also depends a little bit on exactly how you design the input-output relationship. So, for example, if your input is high-dimensional vision inputs, then you want to have a certain type of neural network like convolutional neural networks, which are designed to extract spatial relationships in the images, and then you can train more efficiently. So that is actually a question about the modeling, not about the compute infrastructure, but it's very important for efficiency reasons and parameter sharing and so on. I would say, but the reason why this is also important is because for certain kinds of inputs like vision, you want to have GPU-supported acceleration because vision is very useful for matrix multiplication. That's what CNNs also rely on, basically. To give you a concrete example, right? So in our group, we have a number of servers that we build ourselves with the suppliers. So we don't buy them off the shelf. We speak with the suppliers. We want to make sure that the systems are optimized for deep reinforcement learning pipelines. And the kinds of servers we tend to use have mid-scale GPUs. So they're not super heavy duty GPUs. They tend to be like between 20 and 30 gigs. So not A100s. But that's because the networks that we use tend to be mid-scale, not particularly big. But what's really important for us is that we have very high-powered CPU because a lot of the data collection in the simulation is still run on the CPU environment. And we still have this problem that we need to have very low latency channel between the GPUs and the CPUs because a lot of data transfer happens. The data from the CPU simulation needs to go into the GPU environment to compute the gradients for the policy updates. So that's still a big problem, I find, and that's why we're doing this JAX acceleration now to move everything into the GPU. But it's complicated to program, and it changes the kinds of servers we build. So with the JAX accelerated servers, we now have less emphasis on the CPUs and the CPU cores, and much more emphasis on having high-powered GPUs like 80 gig H100, for example, and it becomes much more expensive. Every server that we, until that point, the previous servers, we had like CPU beasts where with the highest concentrations of CPUs you can actually have on a chip at the moment, which is AMD EPYC chips with, on the motherboard you can fit 2, each with 64 cores. They're all dual threaded, so we can run on one machine 256 parallel threads basically. And we have the mid-scale GPUs. And these machines cost typically between 30 and 50,000 pounds. And now we're looking at systems with not so much CPU, but with the high-powered GPUs, H100s and so on, and then you get into easily like 100,000 pounds. Like GPUs are just really expensive, Yeah, that's just to give you some concrete examples and numbers.
Oh, that's great. Thank you.
So it's not a laptop. Yeah, it's not just a laptop, basically. Yeah.
So my question is about how would you go about using population-based training for common reward and cooperative reinforcement, multi-agent reinforcement learning instead of competitive reinforcement learning?
Same way, yeah.
And you'd play policies against one, like an agent would play its policies against the other. And
yes. I think the only thing you can do is you can remove this word against with. Right? So they're just friends now, not enemies. But for the algorithm, that doesn't matter, basically. You still need to optimize, even if it's a fully cooperative setting. You need to make sure that you optimize with respect to one another. Yeah. So you can replace this word against with respect to one another as maybe a more general term.
Does it scale to multiple agents? Because I feel like the metagame would be like scales exponentially. The size of the metagame would go.
Yeah, scaling is not easy. Yeah. So there has been a lot of follow-up work on PSRO to make it more efficient, more scalable, reduce the sample complexity. There's also, other kinds of techniques, not necessarily PSRO, but which are also population-based training. I just like PSRO because it's a very general and simple to understand approach. So yeah, it's not a particularly efficient way to compute a Nash equilibrium, but it's a very general way that works even for complicated things like partially observable stochastic games, which I think is nice. But yeah, there's certainly more sophisticated ways and more advanced papers, which we don't even talk about here at all.
Yes, from online test. I have noticed more LLMs paper referring to the use of reinforcement learning. For example, OpenAI O1 model was trained with reinforcement learning to perform complex reasoning. Do you think Marl will play an important role in future LLM models?
Yeah, I get this question a lot, and we are beginning to look into foundation-based model type of research as well for autonomous systems. So I'm not sure yet exactly what the roles should be. Clearly, foundation-based models will need to be designed to also exist in a multi-agent setting, so there will be interaction going on. But I think there's two questions here. This question that you just mentioned, I think, is more about using RL as an auxiliary tool to optimize a model that we actually care about, which is the LLM. So the role of RL is kind of diminished a little bit. It becomes this tool, part of the machinery that optimizes this model in some sense. But it's not like we are directly training a policy anymore, which is what we did previously. In some sense, that's how I like to think about it. And then there's the classical approaches when reinforcement learning is directly used to learn this policy. That's not happening anymore in that sense there. So I'm not clear yet exactly. I see how single agent reinforcement learning is used as an auxiliary tool to help improve these, to help fine tune and improve these LLM-based approaches. But I'm not quite sure yet how the unique aspects of multi-agent RL would be useful in that sense. Maybe there's a process where you can say, I want to simultaneously fine-tune a collection of LLMs to do some joint task, and then maybe multi-agent RL could play an interesting role. But it's not something that we've explored yet, and there's probably other people who are further along this research than we are. Yeah, maybe I think I feel I need to catch up on this a little bit as well. So yeah, so maybe not the most satisfying answer. Yeah, but those are my thoughts. Any other questions? Everyone happy with the lecture? So maybe it's time for just a few wrap-up comments. So I want to say, hopefully this was helpful for you. Thank you very much for coming to the course. For me, this was a lot of fun. Time was over so fast. I'm also happy that the slides seem to be going okay. I found some typos, but they've all been fixed. So you can get the slides on the website if you want to go through this yourself later and make sure you look at the book. I want to remind you also that there are these coding exercises, including some ones for today. So you can play with QMIX and VDN. It's very simple to do, but it's good fun. And do the peer discussion on Slack if you want to share experiences or have questions. And let us know if you find any issues with the code on GitHub. Lastly, just an invitation. If you ever come up to Edinburgh, let us know. Be happy to team you up with some guys in the group. They can show you around. It's a beautiful city. It's very popular like Barcelona. And also it's a great university. So do come check it out. And maybe the very last comment is, I've already received some requests like this, but if you work in reinforcement learning and deep reinforcement learning or multi-agent reinforcement learning, and you're looking for partners, or you're looking, maybe to spend some time in our lab, we often host visitors. We often host visitors for PhDs, postdocs, but also sometimes pre-PhD. Then get in touch. All you need to do is just contact me, write a little proposal to explain what you want to do, show that it clearly aligns with our interests. And if you get the funding to come and do the visit, then we'd be happy to host you if it makes sense for both of us. So that's just in the way of a little invitation. So with that said, I think I want to say thank you very much for coming to this course. It was great to meet you, and good luck with your journey in reinforcement learning.